Hi, my name is Mike Holt, and I want to thank you for taking the time to watch this DVD. This is going to be a very interesting and a challenging subject, and we're going to be understanding the basic principles of motor control. But before we get into that, I'd just like to take a moment and give a dedication and thank God for giving me the opportunity to do what I do, to help people, and I hope that I'm making proud of the work that we're going to go here. Before we get actually speaking about the topic, I want to introduce our panel members, and we have 4 different individuals. We have Steve Iron. All right, Steve, tell us a little about yourself.
Mike, I'm from Rapid City, South Dakota, where I went through a formal apprenticeship program, worked as an electrician, as electrical contractor, in electrical wholesale, and then I have taught full-time at a technical school for 19 years, and doing my own classes in exam prep and continuing ed, as well as doing some editorial work to help you out when I'm able to.
Yeah, you've been on the video team many times, and the details of Steve will be inside the textbook. Take a look in there. You'll see a picture and a bio and information how to contact Steve directly if that's something you need to do. Our next team member is going to be Eric Stromberg. Eric, you've been on our team a long time as well. Tell us about yourself.
Well, I started out working as an apprentice electrician while I was going to school. Continued going through school, got a degree in electrical engineering. The job market wasn't great back then, so what I did was I got the opportunity to be an electronic technician for 7 years. And then in 1989, started work for Dow Chemical as an electrical engineer. And then met you about 2000, started teaching.
So you have the background as electrician, then
Electronic technician.
electronic engineering, and then of course you've been with me now for 8 years doing all the different things that we're talking about code, so you really got the package together. Our next guest is going to be Dan Webb. And Dan, tell us about yourself.
I'm a electrical supervisor for a timber products company in Medford, Oregon. I've worked in wood products industries most of my working days. Come up through the ranks, started out as basically a millwright, made it up through electrical supervisor. I teach continued education classes in Oregon. I also teach apprenticeship program.
Okay, appreciate that. Our next guest is going to be Dennis Carlson. Dennis, tell us about yourself.
I'm Dennis Carlson, and been in the trade for probably 28 years, and electrician, residential wireman, electrician, worked on residential, commercial, industrial, and for the past 19 years I've been craft training manager over the electrical division for TIC, the industrial company.
When did you start doing video team members with me? Eric started in 2000.
It's probably been 2002, 2003,
And
somewhere
Steve,
in there.
how long?
2002.
2002. So Eric, you're the veteran right now inside here. All right, our last guest, and he's really not going to be a team member, is going to be Mike Corbett. He's our graphic illustrator. He's the one that actually wrote this particular textbook. And Mike, you've been with me for how long now?
About 25 years.
Yeah, we've been doing this a long time. We argue and we fight code and we fight graphics, and we're a great team. We've done a great
That's the
job.
fun.
We've
That's
done a
the
lot of
fun.
great products. So Mike is the one who actually wrote this textbook. This is the only textbook that I didn't write. Mike is the author of this, so I'm not responsible for anything if it goes wrong.
I was afraid you were going to say
The graphics and everything. I'm talking about me and Mike and the team players and how I play here. You know, this is kind of a strange experience for me because I'm usually the expert. I mean, I write on the code and the calculations, and I'm the guy I'm not the expert in motor control. I mean, I'm an electrician, and I'm like all these other guys. Mike was a journeyman electrician, master electrician. I mean, everybody here has followed the same route, and I'm a journeyman electrician, master electrician. You know what I think is funny? Is a lot of guys look at us in the field, I'm sure every one of us, and they can't relate to us thinking that we were electricians and we were doing that kind of stuff. And it's, you wish you could communicate that. I know people, particularly with me, like, I don't think he was an electrician. So, but what I didn't have, and I still don't have, is I don't have the strength and motor control. So if you watch me and I look like I'm a little stupid here, and I'm asking dumb questions, I'm asking questions that maybe some of you would be asking, and some of your instructors are going to think, well, I know that. I would have thought he know that. So I'm going to be upfront honest with you. I'm not the expert. I'm the facilitator here, but I think we're all going to work together for the purposes of really explaining motor control. And I'm going to go back to our team members, and I'm going to ask them to kind of communicate their first experience with motor control. And I'll give you a couple of my experiences first. The first of my experience, anything had to do with a thermostat. I mean, you have what? A green, a white, a yellow, and a red wire. And then you have this device. And I didn't understand how to connect it in the first place, and I didn't know what the wires did. That was my first experience. And I remember a guy taking a piece of cardboard, and he drew something out, and he showed the W and the R and the G, and he took the thing out and he showed me there's a letter. There's a W, there's R, a G, and a white, green, yellow. And I'm like, but I didn't understand what was going on. My next experience with controls, let's see, it was a two-stage thermostat. Hey, now I know how to hook up a thermostat. Years later, and I'm working in construction. I wasn't in the service, and I didn't do, controls. And my job was to hook up a two-stage thermostat for an air conditioning unit. Now, on a service call, now I'm a service electrician, just became a service electrician, didn't have any service call experience. 4 hours I'm screwing around, hooking up 5 wires to a thermostat. And I never, ever got it to work after 4 hours. And I'll be honest, I got fired because of that. So I love motor control. You can see this. I mean, and that's not my full extent, but that my fear, I sweated. Here I'm a journeyman electrician now. I didn't have the experience. I'm in the field, and I'm freaking out. So, but that's my experience. Let's start with you, Steve. Now, your approach, your experience was different than mine, though.
Yeah, it was different in that I had the training and so on in the classroom before I was actually put into the field to hook one up, but still we have the common characteristics of the drawing a diagram on the cardboard. That's kind of what happens out on the job is, we got to kind of put it into perspective of what do we actually got out here and where are all the parts and how do they hook together.
So, but you weren't intimidated. You were just a little not sure.
Yeah, just a little not sure.
But you had the concepts.
I had the concepts.
What was going to go on. Eric?
Well, I had the concepts, but then it got to the practical problem of field devices. And I don't know if the camera can maybe come up on this. I saw the schematics, but if I look at this button right here, I don't see how to hook up anything. No?
Yeah.
And then, but if I
Keep going.
If I see this button right here, what we have is I can see the contacts through this plexiglass. And so the problem that I had when I started with motor control is that I knew how the schematics were, but I didn't know how to hook the equipment together because I couldn't see the actual parts within them. And I just didn't want to, you talk about feeling, I didn't want to blow anything up. I didn't want to be responsible for damaging equipment.
So now, you understand the concepts, and you were concerned about damaging it, but you just didn't trust that you understood exactly what it was physically doing, electrically doing, and so you weren't comfortable to turn it on.
Right.
You want to get a continuity tester out there or something. You want to be able to check things out to make sure this is doing, this is normally open, this is normally closed, this is doing something.
Exactly.
Dan, your experience?
Mine's probably a little backwards than most because I started out as a millwright, which does all the mechanical, and I had equipment that wasn't working, and I kind of fumbled around until I figured out how to make it work electrically. When I became an apprentice, then it was like somebody had it down in writing. It's that's what we've been doing. So that's just great, for me.
And Dan? Dennis?
Well, when I first really started dealing with it was with the conveyor belt system, and they had emergency pull cord switches and zero speed switches and belt alignment switches and all these different switches on one diagram, and it was just frustrating to not be able to understand how everything kind of tied together and controlled this one motor that controlled this one belt, and it was frustrating. Very frustrating.
Let's ask a question. You guys know what we're going to be covering in the next couple DVDs. When you get done with this book, this DVD, you watch. Oh, by the way, let me talk about this. You want to watch a DVD. Don't sit there and try to follow the book with it. Just sit back, watch the DVD, get the big picture, get the scope and the understanding. Then take your textbook and read the textbook, work the examples, work the practice questions, go through the whole thing and say, because in the DVD, I don't cover everything in the textbook. Also in the DVD, I might have a couple slides or a couple graphics extra that might not be in the textbook. So be a little patient if you see an extra graphic. Don't let that throw you off. You watch a DVD, you're relaxing, you get your textbook, you follow through it. Then I strongly suggest that you watch a DVD again, because then it's like, oh, now it makes sense what Dan was talking about. Oh, now I understand when Dennis said this and why Eric commented. And then you can put it together. But if they watch a DVD, they read the textbook with some of the stuff not covered, if they do the practice question, if they watch a DVD again, how are they going to feel in the field, Dennis, given to your same situation? Are they going to be like still overwhelmed?
In some aspects, but I think once they start getting into it and a little bit more repetition, then I think it'll be.
Is it going to take
it'll become
repetition
easier.
to really be able to have this thing applicable? I mean, if you go one day, one time, and then you don't do it again for a year, and then
Oh
all
yeah,
of
oh yeah, big time. You have to do it several times over and over and over.
Steve, what are your thoughts on there?
Yeah, I agree. There needs to be repetition to, if you just wire up a circuit once and you're a year away from it, you're going to have to come back and revisit that.
You know, let's talk about this. One of the things we hope to achieve in this textbook, not so much a DVD, but in the textbook, is to give you the tools on some common applications. Like Steve said, you know, if you don't do this repetitively, every time you start it again, you're like, what the heck was that supposed to be? The textbook will have a section that, how do you reverse a single-phase motor? How do you hook up the three-phase motor? How do you make a two-wire control circuit? So we'll give you a section, kind of go back and like, oh yeah, and then take that, and Eric, as you show the switches have a number 2 and a 3, and it's like, okay, I remember this. So don't feel like you have to be able to remember it all, but know that there's a resource. This is to give you the concept, to show you that we're all stressed out, we're all not sure all the time, but if you take one step at a time and you get yourself back into it again, even if you've been away from it a while, you're going to be able to put it together. Eric, last
And
comment?
I've got to say that the thing that's absolutely exceptional about this book are the graphics. And in motor control, the thing that's very, very difficult is being able to get a concept of what's going on. And Mike Culbreth has done such an outstanding job of building these graphics that make everything so clear and easy that this is going to become a wonderful reference tool when you look back on it and you say, hey, look, that's in the book. I'm going to get it. It's right here.
That's a key. It's reference. Now, also, this textbook is not going to cover everything. We're just covering the basics. We're just trying to get you started. So don't feel like this is going to be everything you need. But it should be a great reference for you. All right, let's get into some motor control basics. When beginning the study of motor controls are basically different kinds of switches that turn things on and off both manually and automatically. Some of you guys said that this morning in breakfast, you were talking, who was the one that was talking about this, said to you that it was just basically switches? Dennis, I think you're the one?
Well, it's just one of those things that when I first started out, and it was, like I said, frustrating, a gentleman turned around and he told me, he goes, it's just like a switch with a light bulb.
In other words, the load is a light bulb,
Yeah.
the switch is you're turning it on.
And you just got to remember that whenever you look at a ladder diagram or an elementary diagram, it's in its de-energized state.
We're going to talk more about that. So some basic principles is that you're trying to turn on a load, a light bulb,
Right.
and you're using a switch. I mean, think about it. It's an electrical circuit, so you got to be able to close the switch to turn on the load. And the question is, how do you close the switch? Is it done through a computer? Is it going to be done manually? Is it going to be done automatically? Is it going to be done through some kind of external sensor? So that's what we're going to get into. Let's take a look at Chapter 1. Basic principles of motor controls, definitions, abbreviations, symbols, common control equipment devices, and as well as symbols. All right, let's get into it. The concepts of motor control, we're going to be talking about in Unit 1. Motor control language, and the types of wiring diagrams that are used. First thing is the principles. Motor control circuits and equipment permit the use of smaller conductors, cables, and raceways. Control equipment can also have a much lower ampere rating. Here's what we have. We have this motor. Now this motor is going to be, in this case here, I don't know what it's going to be. I can't say what size fuses, but let's just assume this was 60 amp fuses. Well, if we're trying to control this by a push button over here, because we're trying to have some kind of convenient control, instead of me running wires and putting a 60 amp disconnect over here, I'm able to use some small control wires that can control, well, this case here happens to be a motor starter, so we can use smaller wires for controls, smaller raceways, and we also have a lot of control to be able to turn this motor on or to turn the motor off. Is there a particular size wire that's a common practice, guys? Dan, what do you guys use for like a control circuit if it's not computer control?
We generally use 16 AWG.
So your push buttons would be 16, would be, control wiring.
Yes.
Eric, do you use a larger wire in yours?
We typically use 12 gauge because of distances, unless it's part of an assembly and it's already 14.
Okay, so it's a lot smaller than the power conductors
Right.
involved with the motor. Either way, however, and we'll talk about those details as to how do you size it. But the concept and the principle of controls is you want to be able to take a load, and it doesn't have to be a motor, obviously. You want to take a load, and you want to be able to do something with the load. You might want to tie it with a computer that when this load starts, it starts a process, and then we want to go with this one, and then we want to do this, and we might want to provide some signaling. Okay, well, is the load on, and how much is it drawing, and is there water in that container, or the liquid? What's the level of that? And that affects, well, how much grain, and we want to make sure that we have a mixture, that we have so much of this versus this and this, and we want to be able to mix it up, and then you got to wait till it all fills up, and then you got to turn it. You can see there's a million combinations, and what an exciting opportunity to be able to control things through, and eventually, once you get the basic controls operating, and Dan, I think you guys, is it almost all with computers? Your
Yes,
controls?
we have computer PLC control on all of our equipment.
Yeah, so I mean, we'll talk about that. You're in the sawmill industry. So this, the wood comes in, it gets cut up, all this stuff gets processed, and a lot of these things gets in a process. So in order for all of this to work, the controls offer flexibility. We need to make sure that it says that in the book. You have flexibility. You are able to manage and manipulate things and make things work as a cohesive system, or simply turn something on, turn it off. But it's all turning it on and off, but it's a matter of sensing it, reacting to it, signaling it, putting it together with smaller conductors than it would take. All right, let's go on a little further. Motor control circuits can be of lower voltages than the motor to make it safer. So here's an example where we have a 480 volt. Don't worry about all the details here. You're going to be able to read this later on. But this is line 1, line 2, line 3. This is the power coming into the motor, and it's going to be 480 volts. We can take a voltmeter between line 1 and line 2. It's 480 volts. But maybe if we kind of go back a couple slides, we don't want this guy working on 480 volts right here, because right now in this example, if this was a 480 volt application, we're tying in to this line 1 right here on this one fuse, and now, well, this one happens to be, well, it's one fuse. I'm not sure where the voltage is going to be, but let's just say this was 480, then this push button will be 480. Now, do you guys, Eric, keep your control voltages at a certain voltage and Dow Chemical, or whatever it is whatever it is? Is there a practice?
Right, our control voltages are typically 120 volts.
Okay, so therefore, if that is your practice, if you got a 480 volt application, like what we have here, then you're going to put a transformer, step it down from 480 down to 120, then we can have lower voltage. I'm making an assumption. We all are making this assumption. We assume that you understand basic electrical theory. What I mean by that, you know what Ohm's law is. You know what a series circuit is. You know how they operate. You know the laws of series circuits. You know the laws of parallel circuits. You understand magnetism, electromagnetic coils, relays. And you need to have a strong foundation. If you don't have that foundation, I'm not trying to sell you something. You need to get our theory book. You need to get the theory DVD. You need to complete that first. It isn't going to be fair to you to sit down, watch this DVD, go to the textbook, and you don't even realize that you're uncomfortable. You don't know why. What it is because you don't have the foundation and the basic that it takes to get to this level. Take a look at this graphic right here. If you look at this graphic here, some of the things that you should be able to understand already. You should understand that this is a transformer and the concepts of transformers, and you should understand what an overcurrent protection device is, what a fuse is, what a circuit breaker is, how they operate, how electrical circuits operate, how voltmeters operate. All these are fundamental givens that we are assuming, not how how that circuit worked, but understand the fundamentals of electricity. Steve?
Just on the safety side, Mike, there are a lot of circuits that a majority of them probably are lower voltage using like the 120 that you're showing or a PLC, but there are circuits out there that do use the 480 volt control. So we want to really caution the guys to be careful and test that voltage and know what they're working on. I worked on old sawmills that were all 480 volt controls, and they're a widowmaker.
And now, and with controls, you could use any voltage you want to use. It's a matter of design. I mean, you say, hey, we got 40 there. We're not going to put a transformer. We're just going to go with the 40 volts. And then somebody's like, no, we want to go to 120. And some people say, hey, we got computers here. We're going to be able to drop that down to much lower voltages because we're using electronics to make it happen. So Steve is bringing out, we'll talk a lot about this later on as we go along, and it has to do with electrical safety. Make sure it's safe. All right, let's move on. All right, controls consist of computerized systems, solid-state logic controls, programmable logic controllers. We are not going to be talking about logic, programmable controllers, or any of that. So right at the beginning, and you're like, well, wait a minute now. What's the sense of me getting a motor control book or a DVD today in whatever year this is, and it's not covering that stuff? Nope. No, we're covering the fundamental and basics. And I checked with you guys, the experts, when we talked about last night and this morning. Am I right? This is, Dan, you work with PLCs every day, don't you?
Yeah.
That's your life.
I do.
Now,
we have PLCs plus computer interfaces that have graphic controls, but the basic relay ladder logic start-stop station is used in our PLCs. I mean, that concept is used throughout everything we do.
how do I, as an electrician, take this course, learn the basics, get an understanding? How do I get into the area of PLCs? How do I learn that and be able to then, I mean, how do I do that? How do I do as an electrician?
Well, you need to walk before you can run, and
Wow.
using this relay ladder logic and understanding controls and the interface devices and whatnot, you know, photo eyes, float switches, you need to understand that before you can bring them into a PLC and then do the...
But where do I get the classes? Because you call Mike Holt. No, we don't have it. Well, I thought you had everything. Okay, we don't have the books. We don't have the DVDs. We don't have the classes. So how do the guys watch this DVD get into programmable controllers? The engineers or the electricians? Or
There is a couple other companies out there that do offer motor controls, and it's a hands-on class where they have simulators that you can actually work with, and then also PLC classes.
But I'm saying the PLC classes.
Yeah, you can get industry classes. Sometimes trade schools will have a
Right.
class on PLCs, but there are some subtle differences from manufacturer to manufacturer. A lot of the manufacturers do have their own
So
training
Allen
classes.
Bradley is
Allen
going to
Bradley
have
training
a class,
yeah.
and they're going to have a training program and explain how their ladder logic works and how their products interface. So the key is this. If you want to get in programmable controllers, or PLCs, programmable logic controllers, then you're going to need to get with the manufacturers and find out about their classes. And some of you watching this DVD is interested in that. And that's where you're going to get to the next stage you're going to go to. All right, let's move on. Motor control equipment. There are two basic designs of motor control equipment, NEMA and IEC. NEMA is the National Electrical Manufacturers Association. It's going to be heavy-duty equipment. Maybe some of you guys can get one of those NEMA devices ready for us to take a look at, and the camera can zoom in tight when we get to that. It's used in a broad range of applications, and it's commonly used in North America. And that's going to be NEMA. Let's take a look at IEC controls. Is the International Electrical Technical Commission. It's less expensive, smaller in size, tailored for specific applications or specific requirements, widely used in Europe and Asia. All right, let's take a look at it. So the one on the left of the two, that would be your NEMA. Look at the big wire.
Well, this is NEMA.
Yeah, it's my left, I'm sorry.
Okay.
The camera's left. That would be NEMA. You can see the big wire on there, you can see the equipment. Now the one on the right is going to be IEC. Smaller, basically equivalent, same size. Give me some feedback, guys, as to, Eric, you're an international company. Do you guys use one standard versus the other, or whatever you guys can
we
find?
use whatever standard the country calls for. I like to say that IEC is built for use and NEMA is built for abuse. So with NEMA, you have a 100 amp contactor, put 120 amps through it all day, no problem. IEC, put 103 amps through it, you buy a new contactor. And so it all boils down to knowing what the application is, knowing what you're doing, and applying products intelligently, and you'll be fine.
Dan, what do you guys use, NEMA or IEC?
Everything new we put in, because I work in the mill environment, industrial, we try to stay with NEMA because we do abuse our equipment as much as we can.
Okay, all right. Dennis?
NEMA, typically NEMA. I mean, some of the newer equipment you're going to see IEC, but It's
Steve, when you were teaching and when you were out there, what do you think?
Well, when I was wiring more NEMA, but anymore it's hard on the smaller sizes to even get NEMA, and the IEC is so cost competitive. But one thing that's really brings us down, like Eric was saying, I've seen a video done by one of the fuse companies showing a IEC type of contactor being subjected to fault current in excess of its rating, and it just vaporizes. Just
Okay.
vaporizes. So showing the importance of using a low peak fuse to
Okay.
protect them.
All right. Point is, there's different standards. The NEMA standard, IEC standard, you kind of got the feedback. We don't even really know any more than that, but let's move on. Let's now talk about language, electrical symbols, words, line diagrams that explains the operation of the motor control circuit. You know what? I'm not quite sure whether this is the right name, motor control, because we might not be controlling motors. Right? We might be actually having signaling. We might be like turning on a light or an alarm. So really, this is more of controls. We might be controlling lighting. We might be controlling motors. We might be controlling processes. So I'm not sure if I like the word motor control. I'm going to try to work on controls and signaling as we go along. The symbols represent devices, power conductors, control conductors, and conductor connections, as well as terminals. Types of control circuits would be ladder diagrams, connection diagrams, pictorial diagrams. All right, let's talk about what we just were saying, all those words. This is a diagram, and it's called a ladder diagram. And the reason it's called a ladder diagram because we have line 1 on the left, we have line 2 on the right, and if we ran line 1 all the way down, line 2 all the way down, and we ran line 1 all the way down, we could now go ahead and make a connection from line 1 to line 2 and put another set of controls here that could do something else. So we're basically connecting with it. So now these are some symbols. We'll talk about this is a stop button. Oh, how do I know that? Well, because it says stop. This is a start button. Again, it says start. Now you got some contacts here, which we'll discuss a little bit more, and then you have some other things. We're not going to worry about that right now. But this, what you're looking at, is a ladder diagram. It's also called a line diagram or an elementary diagram. It's representing the function of the control circuit and associated devices. Again, I don't want you getting too detailed right now. I just want you to like, oh, that's a ladder diagram. You don't know what it means, but you can say, that's a ladder diagram. That's all I'm looking for right now, so relax. Let's take a look at a connection diagram. Now we had the ladder diagram. Now we have a connection diagram. And for convenience purposes, we put some numbers on this connection point. That's connection point 1, that's connection point 2, connection point 3. And then we have this start, stop, and that's going to show connection to point 1, connection point 2, and 3. So this is a connection diagram. Again, not trying to have you read it, just try to say it. Okay, I understand what a ladder diagram looks like. Okay, let's take a look at this. I understand what a connection diagram looks like. All right, let's move on to the next one. Now, pictorial. Okay, well, this wire here, we'll call that terminal point 1. That connects over to line 1. And then we have a contact here. We haven't talked about contacts yet, so I'm not going to get into detail. I want to, but I can't. Let's just say this is a pictorial diagram showing you kind of like, this is something like, Dennis, that you kind of created, where you actually put this together. I mean, you put your little contactor together, and then you have your start, stop button. So this would be something, Steve, you do like in a lab, right?
Right.
This is actually run this wire here and put this wire there and put this wire here, connect the wire there. Well, then that's what it looks like pictorially. In reality, the start, stop button might be who knows where it's going to be, but pictorially, we can see how it all fits together. And the next one is going to be hand-drawn diagrams. This is the one I enjoy the most. I think we all kind of like, okay, because I think a hand-drawn diagram, when you put it in the field, is because you don't have this page with all the stuff. You start with a blank page and say, okay, here's a light, here's the neutral, here's the hot wire, here's the switch, close, okay, got that. Okay, now let's add the next element and the next element. So take a look here. You kind of draw this out, and you kind of go on a piece of cardboard and a piece of keel or on the floor of a concrete slab, you know what I mean? And then you kind of like draw it out. So the different ways. Let's review this again. ladder diagrams, connection diagrams, pictorials, hand-drawn. Now, hand-drawn is kind of obvious. We know that we do that in the field. Pictorial is probably something you're going to show in a book. Like you were saying, Eric, these are great pictures you can see. The schematic diagrams or the connection diagrams, that's what you're going to see, what, on the manufacturer's literature?
Yeah.
And then where do you see the ladder diagrams?
Engineer, from the engineer typically.
So that would be in the engineering plans. Now, Dan, is that what you use, the ladder diagrams for programmable controllers?
The ladder diagram is what we use 99% of the time for hardwired as well as for relay ladder logic.
Okay. You know, if you feel compelled, if you want to, you might want to stop the DVD, say, hey, that wasn't too bad. Then stop the DVD right now. Take a break. Go back, read Unit 1. Work out the practice questions for Unit 1. You might want to say, you know what, I'm going to just rewind the DVD again. So you decide whether you want to watch the whole DVD, whether you read the unit or the units, or whether you want to do one unit at a time. You're the control. How would you guys do it personally? Let me tell you how I would do it. If I was watching this, I watch the DVD, I'm thinking, that's easy. I'm not that intimidated. I have the basic concept. These guys give me some confidence. I think I would read the unit again, work out the practice questions, and I'd watch the DVD again. That's the way I would do it, because I know how my brain thinks. I like to take a piece at a time and master that, and then if I'm confused, then I'd be able to see that part and not wait till I'm overwhelmed. But everybody's different. How would you guys, Steve?
Yeah, I think it'd be real good to, like you say, go to the book and then do those questions now, and that way it'll really kind of help internalize what you've covered already. If they do the questions, stop and think about it before they go on to more material.
Eric?
Well, to me, learning's like a staircase. I mean, you learn a little bit of philosophy, and then you put it in practice. You learn a little bit of philosophy, put it in practice, a little bit of philosophy, put it in practice. So it's a repetitious cycle, and that's just the best way of learning.
And if you have somebody you know that you can review Unit 1 with also and ask them some questions, an instructor or maybe somebody in the field who has more experience, Dan?
Yeah, these graphics are so great. I think go into the book, and once you learn this basic building block, then you can grow from there.
Probably watching the DVD and at the same time using the book and going
Okay.
through the book. And then, at least then I could turn around and stop the DVD.
I gotcha.
And if there's something else more in the book itself, I could stop and read it. And then I could either rewind the DVD or continue going forward.
And I do need to remind everybody watching DVD that we're not covering everything in the book in the DVD, because there's a lot of content that we just can't cover in the DVD that you're going to have to read, and then your practice questions take you there. All right, you decide. You might want to put this on pause, do whatever you think is the best thing to do, or continue on. Let's go on now to Unit number 2, definitions, abbreviations, and symbols. All right, let's go into definitions of control terminology first. It's real important. Now, we're not going to be covering any definitions in the DVD. There's a huge number of definitions. So you're going to have to take a couple minutes, do a quick review of the definitions before we go a little further so you understand what's going on. And just lightly go through that, because when you get a little further in it, you're going to go back to the definitions later on. So we're not going to be covering definitions. Common abbreviations, same thing in the textbook. There's no standard set of abbreviations, but those contained in our textbook are probably the most commonly used and widely accepted. But I mean, people are going to make up their own abbreviations as they go along. So be sure you go into the textbook, look at the abbreviations, get a kind of feel for that. But for the purpose of the DVD, we're pretty much going to be explaining everything we're going to be going along. Standard symbols. Now, we'll be spending some time on symbols, not all of them, but there are a lot of different symbols and connection points and conductors related to controls that's in the textbook. And here's an example of one slide that says, okay, it's a single circuit, momentary contact. So, okay, that's a momentary contact. Probably should have a maintain. I guess we probably need to draw a line between the two of those so that we know that that's momentary over here. Got that? Okay. This is maintain, means that if you press one, the other one goes the opposite direction. Is that right? And if you So this is what? You push this down, it does something else. So am I right about this or wrong? What's this right here? Maintained.
That would be a mechanically interlocked switch. So when you switch one, then it would be...
Okay, that's what.
Like a single pole switch.
Okay. And here, 2 position, 3 position, whatever it is. These are just symbols. Not connected, connected, wire. All we're looking for, again, remember, relax. All you have to say, oh, those are symbols. Do you know what any of the symbols mean? No, that's okay. That's all we're looking for. You know that that's a symbol, there's an abbreviation, there's some list of terms, there's some definitions. Next slide is what? More symbols. We're not going to look at them now, but you need to go back to them later on. And then another slide, well, table, more symbols. We're not worried about the symbols. Eric,
I
what are you
do
going to
need to bring up a point of caution. With as much international equipment as we're seeing today,
Yeah.
a lot of the international equipment comes with the schematics from that country. So just be careful, because something, if you get used to a symbol in the United States, you might think that it means the same thing from another country, and it doesn't. So
Well,
just be careful with the legends.
Good point. Color coding in the United States, we use certain colors. Well, China uses green as a hot conductor.
Right.
So internationally, we got to be real careful when you're getting equipment from other countries, and control brings another level of caution. Here's the next slide here. This is a pictorial, right? We learned that already. And this is a ladder diagram. And all I'm trying to show you is that this switch right here, the symbol of that switch looks like this. And this contact right here, there's a coil inside this particular contactor, and that would be the symbol. So we're not getting any further other than, oh yeah, that's a pictorial. Oh, that's a line diagram. Oh, these are symbols. And how do you know? This is a connection point. How do you know that? Well, let's go back here. There's a switch, right? And then we had something with a circle. Let's see if we have a picture of that here. Right here. This would be a coil. So you can see how they relate to. In addition to symbols used in control schematics, manufacturers use additional symbols in their catalogs and other literature to aid in the selection of the type of control devices. And we probably need to put an author's comment in the textbook, Eric, that you brought out. Not only did different manufacturers, but symbols internationally might not be used the same as we use in the United States. Well, that was a fast unit number 2. Stop, read them, take a look at the textbook, and then continue on to unit number 3. Let's go. Common control equipment, devices, and symbols. This unit covers relays and switches, their operation, and the symbols that relate to them. All right, first thing is a term called an auxiliary contact. Now, auxiliary contact would be right here. But that's not important. What's important is that there's a symbol for that, and that would be a symbol for an auxiliary contact right there. Would this be, this wouldn't be considered, is this a symbol right here, guys? Would that be a symbol also? Or is this the symbol right here? Dan, which one do you think is the symbol? This is just the actual, I guess that's a symbol also, right? That has to be a symbol.
Yeah.
This is the physical one. It's either, here's your contacts. Normally open contacts, we'll talk about that, normally close. And Eric, I think you're the one that made a little comment that we kind of like, I don't say brush off, but we said that when you're looking at a ladder diagram, or when you're looking at any diagram, you're looking at it under the condition that it is de-energized. Is that what you said?
Well, Dennis made that comment,
Oh,
but
Dennis?
yeah, that's a standard tenet of electrical schematics. Everything is de-energized
So-
or shelf position.
Okay, so again, we're not getting into detail other than, hey, there's a term called auxiliary contact. That's what the symbol looks like. All we're doing right now is trying to put together some terms, showing you symbols, because these are the terms that we're going to be using quite frequently. Steve?
Just one comment about that the word auxiliary means that it's not the main contacts, that it's in addition to the main, which you can also see in this diagram.
Okay, I like that. That's great stuff you brought out. In other words, there are, which people don't know this yet, but inside this motor starter, there are 3 main contacts. In other words, this is a switch, isn't it?
Yeah.
That somehow we're going to close this switch. And when we close the switch, the 3 main contacts are going to take power from line 1, and it's going to present power to terminal 1. Power from line 2, power goes to terminal 2. Line 3, power goes to terminal 3. And now there's lots of things happening inside here, but the basic concept is this is a switch. And if everything goes right, and there's a coil here that will draw in the contacts, it's going to be done with electromagnetic field. And when that thing gets closed, there are contacts that are auxiliary in addition to the main contacts. And that is your auxiliary set of contacts. And that's what it looks like as a symbol on the wiring diagram. and that is the symbol on the ladder diagram. And by the way, this would be the main contacts, 1, 2, 3, and this would be the auxiliary contacts.
And those auxiliaries kind of look like they're just sort of stuck on the side of that starter, which in some cases may be the actual. You can add more auxiliaries on
So you can add an auxiliary onto an auxiliary?
in many cases, depending on the starter. You can add more blocks on there with more
Now,
auxiliaries.
if you add more blocks on there, because the way this works is that if we energize this coil, we're gonna draw the armature in, and in this case here, we would end up, if we energize this coil, we close main 1 contact, main 2 contact. We call the main contacts 1, 2, and 3 will close. We will then provide power to the motor, right?
Right.
And when we close these contacts, and like Dennis said, these are shown no power, but if they are powered, then that means that the contact point 2 and 3 would close, and contacts point 4 and 5 would open.
Correct.
Because they're going to go into a different state. My question is, if I add auxiliary contacts to it, do they also react the same way that whatever, in other words, I could stack another one over here, and if
Exactly.
you would look at them in the de-energized state, and if it becomes energized, so somehow they're going to be connecting together, but they're going to be, this one coil is going to then continuously affect all the contacts and change their state. Okay? Did a little bit of work here, more than I plan on this particular page, but I like it. So we understand what an auxiliary contact is. Okay, fortunate we brought a bunch of products. A lot of you guys brought a lot of products with us. And Dennis, you got some products there to show us there. Show us, we're talking about auxiliary contact. Where would that be at?
Well, these are the auxiliary contacts right here. There's normally open, normally closed on this side. There's normally open on this side. And then I could actually add another normally open right into this spot right here.
Okay?
And so just slap it in.
All right, let's go to the next one. And you know, we'll keep pulling in product as we go along. Let's talk about relays. A relay is basically a switch that is activated electrically. And if you guys can find a good relay there, then we'll show that in a second. Here's what it looks like. Again, we assume you have electrical theory background. Here would be, I think we'd call this like line 1, and then it would go to the load, and it would be T1 off of here. And then we have a coil, and this is the control circuit. This control circuit right here could be 24 volts, it could be 120 volts, it could be 240 volts. We talked about the different voltages. And if we put an electric circuit here and energize this magnetic field is going to draw in this metal here, and it's going to then close this contact. So here you have coming in, line 1, contact closes, it goes over to T1, and then we operate the relay. So a relay consists of a coil and a set of contacts. Here would be a symbol of a relay. And it might be an M coil, it might be a CR, which is a controlling relay. So now the relay has a coil, which is right here, and the relay has contacts. In our case right now, this is showing a de-energized state. So we have a set of normally open contacts. But there could have been an additional set of contacts added, which would be normally closed. I think we did a good job on that one. This is a symbol of a solenoid. By the way, this is a symbol of a coil and the contacts, and combined is a relay. This is a symbol of a solenoid, which just means that this is where the control wiring goes here. If you energize, we'll probably put a terminal here. I'm not quite sure. We can put it in 1 and 2 or something like that, whatever. But if you put your control wiring here, probably put a couple wires off of here and just indicate that that's control wire. That if we energize this coil at whatever voltage the coil is rated, then what it's going to do is it's going to take this plunger and it's going to draw this armature in. It's called the armature. So you have your coil, your magnetic field, you have the armature, you energize this coil, it's going to draw this plunger in. Again, we're not getting into too many details, but we're slowly starting to migrate in there. But we're just really talking about symbols. So you can take a look at a symbol. Okay, that's a solenoid, but you have to understand the concept of a solenoid, how it operates, the concept of relay, how it operates. Let's go back to the slide again. So there is your symbol of a solenoid. A drum switch has a handle which is manually rotated either left or right to change the contacts within the switch. So here's your drum switch. So we have a set of fixed contacts. And then we have a rotating drum. And there's your symbol. And somehow you have line 1 goes to 2 in this case here, and line 3 goes over to this terminal 2, and line 2 goes over to this terminal 6, and then the instructions tell you that connect one phase of the motor to T1, and T1 goes to terminal 1, and T3 goes over to terminal 4, and then T2 goes over to terminal 5. Now, are these switches going to be numbered like this here, or is this just for the purposes of this class? Is there a practice? You guys have any feelings?
This is just for the purpose of this class. I mean, you have to demonstrate. You look at the symbol, and then you understand the function, and then whatever materials you have in the field, you make it happen.
Okay.
Yeah. The thing that's critical is the chart, because every manufacturer, there's not a standard numbering or a standard configuration. You'll get drum switches that switch left to right or vertically or horizontally, and you have to follow that chart to see how that particular switch is going to operate. It'll have the numbers or labeling on it, but then you have to go with the chart and see what's going to happen inside.
So if we understand that all we want to do is we want this motor to run in this particular case, and we're using a drum switch, that if we want from line 1 to go to T1, and line 2 to go to T2, and line 3 to go to T3, then we would have to go between these 2 points, these 2 points, these 2 points. So let's say we want, if they were numbered, let's say, then I'd want to go to 1 and 2. So then, okay, 1 and 2, 1 and 2, 1 and 2, 3 and 4, 3 and 4, 5 and 6.
Yeah.
So right now, the way this is set up, if this were the case, maybe there's another set of 3 more leads. Is that right? That maybe has a motor, or it might change it. Oh, 1 second. 1
See,
and
that's
2.
your reverse position. Those are the continuities inside the switch.
Okay, that's
And then
how
when
it's
you
going to go.
Yeah, and then when you go to the forward position, the far right-hand side gives you the continuities. It switches to how those are connected.
And I want to make sure that we do come back to this slide when we start talking about reversing motor, guys. So remind me to capture this slide to pick this up, that we can use that later on. Okay, let's back off. I'm getting a little detail. Getting more need to be done. Let's go back again. This is a drum switch. These is a symbol. This is a symbol of a drum switch. Let's go a little further. Now, drum switches can be used to make and break numerous connections which allow functions like motor starting, stopping, reversing, and braking to be all done by one device. Now, Dan, how common is drum switches in your world?
Drum switches normally would come on very small equipment, maybe like a wood lathe, and big equipment. They're not readily used anymore.
Now, I said you were in a sawmill, but you corrected me at break time. So you're in a what mill? Let's get
I work at a hardwoods plywood mill and a particle board plant
Okay.
where we make composite panels.
Okay. So I'm sorry about that. All right. So when do you use drum switches? What's the most common application for drum switches, Dennis?
Well, like Dan said, wood lace, metal lace, that's typically where you're going to see them. And I think, Steve, you said another location.
Yeah, one place where I've seen them used is in agricultural for raising and lowering the silage auger into a silo to bring it down to the silage or raise it up. You're going to use a drum switch and watch your amp meter to make sure you're loading your auger. As you
I have
lower
to tell
it.
you a story where I use a drum switch. Had a drum switch on my boat lift that when you turn it this way, it would drop the boat down. It's a single-phase motor that had reversing, which we're talking about, and then when you turn it the other way, it would raise it up. And every 2 or 3 years, I would ski, and I'd come back after skiing for a couple hours because I barefoot water ski very competitively, and I'd smell like this burnt-out motor smell, and my motor burnt out. And my lift would be all the way up on the top. I'm like, what the heck's going on? I thought I dropped the motor when I went skiing. Whatever. Motor burns out, spend $400, get a new motor, stick it in there, everything's fine. 2 or 3 years go by. Smell that common smell. The motor's back up again. I'm thinking, what the heck's going on? And then one time, 3 times I replaced the motor. We'll talk about overload protection when we get into motors, okay? This is leading up to overload protection, which I did not have in the motors in there. I finally found that on this drum switch, the way it was set up, there was a piece of angle iron, little aluminum angle iron, that you could use to kind of like bring it down, like a little string. You know how you tie a string on it? So while you're down in the boat, in the water, down the dock, you just kind of pull the string this way and it would go down and up. Well, a bird would fly, would land on one side of the drum switch while I'm out there skiing. as soon as it lands on there, it goes down. The bird says, hey, what the heck? The bird takes off, and it burns up my motors. So I learned about drum switches in that process. There's an application, but the next level of we're going to learn is about overload protection and how you could save $1,200 in protecting 3 motors. So that's a drum switch story, and I'm sticking with it. Let's move on to float switches. A float switch is used to start and stop a motor in order to control the level of a liquid. Let's take a look at this here. This looks like a lot of work. I mean, this looks like a float switch. Man, that's a lot of, well, whatever. Okay, we don't have the wiring connection shown inside here, which maybe we don't have to have, but it'd probably be helpful to show that you'd bring a conduit in, maybe like a piece of liquid in, and looks like you have a symbol here to be like, one goes in and one goes out, 2 wires coming in here. And as this water level rises, I guess this could be a sump pump, right? If you're in a basement and the water level rises, it would go up. And since these symbols are all shown de-energized, or no state at all, that if the water level rises, this normally open contact as this rises would close. And at the same time, it might have 2 sets of contacts, a normally open and a normally close, NO and NC, that as this water level, the liquid level rises, it closes a set of contacts. At the same time, it would open a set of contacts. So in our example here, I wanted that if it rises, I want it to close contacts, and those closed contacts then could be used to turn on a motor to pump out the liquid in there. Float switches operate on air or liquid by the movement. Oh, that's a flow switch. Before I get off, I want to stay on float switches. Dan, you had a float switch there. Show us.
Yeah, we have an example of a float switch here. This one could either actuate on rise.
Hold on one second. So if it rose, that would be like for a sump pump, right? As it rose.
Yep, as it rose, it would turn on.
Now, one second. Could I put that, looks like I could put that in an LB, right? Looks like there's what, half-inch threaded entries in there,
Yes.
and you got your 2 wires. Show us the 2 wires.
Yes.
All right, so I have the 2 wires. If I put that on an LB, just stick it in the basement area, as the water raised up, it would open a set of it would close a set of contacts, right?
Yes, this is actually made to go into a vessel, but
Okay. I'll go.
that's
So
why
I
it's
see what you're
threaded
saying.
on this
Okay.
side, so you would thread it in.
I see what you're saying. Go in the vessel.
And then vice versa, if you wanted to use it on as a
Oh, okay.
as
That's
it
a different one.
fills, then you wanted to turn it on until it
Okay, that one
empties.
would turn it on when you raise it up.
Yes.
And because there has to be a set of magnets in there making those contacts
Yes.
close. Turn it the other way. That one would have the contacts closed.
Would actually break it.
It
when
would then
goes up.
open the contacts as it raised. It would remove the magnet from closing those contacts. Now, does that have any kind of ampere rating or voltage rating? Is there anything marked on
Yes,
that?
this would be pilot duty only, which means that it can only be used in control circuits. You'd want to run to a relay or a contactor.
Oh, so what we're looking here on the graphic here, and I said, man, this is awful a lot of work. This would not be a pilot duty. I could run like 14 gauge wire and making break contacts to turn off a motor. Where what you're showing us is something that would be making break contacts of a control circuit. You use the word pilot duty. Is that a common term used in industry?
Yes. Yes.
What does pilot mean? Is there anything particular reason that says pilot duty? Is that just a practice
That
term?
it's used for control circuits.
Okay, well, there you go. All right, good. Let's go to flow switches. Flow switches operate on air or liquid by the movement of a paddle to activate the contact. That's a symbol. Here's your paddle, and that's where it threads in. Here's some movement air. And you kind of thread that baby right inside there. Maybe they both should look the same right here. And air moves this way, moves a paddle. When it moves a paddle, if there's no movement, then the contact would be open, is that right? And movement would close the contact. And if there's no movement, this contact is normally closed. But if there is movement, then it opens. So by having, is it standard practice that most of these contacts come both normally open and normally closed? In other words, the standard practice is that they would be a normally, like the float switch you showed us, Dan.
Yes.
It had both conditions. You turn it this way, it's one way. Turn it that way, it's the other way. That way you have, is that a common practice, guys? That you're pretty much going to get them
Yes.
both?
It kind of reduces the inventory that your wholesaler has to carry if you can use the same device for either to get
Well, you know,
normally open or normally closed
A
contacts.
flow switch would be, I would assume, used like in a fire pump to know that, you know what, there's water being moved. A sprinkler, so I know that, hey, the sprinklers are operating, or I guess any combination of a
Yeah.
million applications where we're trying to determine whether there is a movement of air, a movement of liquids, or anything else. Do we have any flow switches? Yes, Dan?
I was just going to say an irrigation pump where you want to make sure that pump is not pumping dry and burning up your motor.
Oh, that's
That way
a
you make
perfect
sure you've established flow on it.
Oh, there's a perfect example. What you're saying is that, okay, that when this motor starts, we better expect flow and maybe some kind of delay, that if we don't get flow within a real short period of time, then we recognize that we're not getting flow after this started, well, then turn it off.
Yeah.
So that's an example where we're starting to tie in controls. Eric, you going to say something?
Also, an example of a flow switch can be in personnel safety. If there's a safety shower and some person has a chemical on them, foreign substance, goes into a safety shower and turns the safety shower on, you might have a flow switch in there to indicate back to the operations center that water's been activated, you better go check it out.
Okay, excellent. Limit switches, mechanical switches. I know we have a bunch of those. We'll show those in a second. Limit switches in process automation is used to sense mechanical situations to control the motor's function. And here's a limit switch right here. That's what it looks like. And this is a lever actuated. And this is a roller, a push roller actuator, and that's a fork. So there's different ways of sensing it. And here's what it looks like. That symbol, we're talking about symbols, that's normally open, limit switch, and that's a normally closed limit switch, and they're all basically combined together. And then here's another one. What's the difference? What's the difference between line under and line over, guys? Is there anything, does that mean something?
Yeah, it does.
Tell me why, what's the importance of that?
With the line under, that limit switch has to be raised to make contact, but with the line over...
Hold on, okay. With the line under, the limit switch...
It's normally open, and so it has to be raised to make contact.
Oh, I'm sorry. This is normally open.
Yeah, and the one on
But-
the right is normally closed.
Oh, okay.
And so
I thought
they're
this
showing-
was normally open, normally closed. Okay, this is just a normally open contact, that as you raise it up, you're closing it.
Yeah. But see,
Okay.
the distinction is the one in B, the one on the bottom is normally open being held closed, and the line is underneath the dot. But
Okay,
in the top
it's
one,
normally open.
when you're holding it closed, the line is under the dot, but if it's a normally closed, the line is over the dot.
Okay, this is normally open, okay?
But it's being held closed in the bottom part.
But it's being held closed. In other
So
words,
you-
this actuator got moved.
Right. You're drawing the drawing when you're at one end of your travel, and your conveyor, your mechanism, whatever is holding that switch in the closed position.
Right. And then on this side,
That
the
one's
same.
just normally
but
closed.
both this one and this one are both in one device, the top ones. And then if all of a sudden you get to the end of something, it goes from normally closed to now normally closed, held open.
Yeah. But
Dennis?
the line being above the dot tells you it's the normally closed. The line below the dot tells you it's the normally open.
Gotcha. Dennis, what you got there? You got some
Yeah,
limits?
we just got two different limit switches here. I mean, they're both made by the same manufacturer, and just what your pictorial shows. The same,
So one goes
same
down,
kind of
one
thing.
goes that direction, and one goes the other direction.
Right.
Let me see the other limit switch. What's the other one? 1 second. They
It's
have
basically the same thing. What you're talking about on the normally open, held closed, would be if you had this up against something, your normally open contact would be made, and then if that went away, then
Right.
you would go back to your...
So it's a normally open contact that's just that's closed, right?
Yes, it would be held
Might not
closed.
necessarily held
if it's
closed, but I
under
mean it's
load.
closed. But in
Yes.
this case here, it's showing that it's being held closed.
Yes.
Now, are those voltage amperage ratings on those limit switches?
Yes. This one's 10 amp, 120, 240 volt or 480 volt, 1/3 horsepower, 120, 3/4 horsepower, 240 volt, 0.8 at 115 volt DC, 4 amp at 230 volt DC.
All right, so low motors or control circuit.
This one actually says 600 volt AC maximum pilot duty.
Yeah.
Oh, it says pilot duties. That's
Heavy-
where the word came from.
Heavy duty NEMA A600,
Okay.
10 amps.
Eric?
Well, actually, you know, when you're talking about your boat hoist, this is what you needed on your boat hoist.
Yeah.
Because when the hoist
point.
got all the way up to the top, then it would have shut itself off. Now, what you've also done here in this example is you've told the students why this stuff is worth learning. Because it is the power of knowledge versus the pain of learning. Learning is painful, but if learning saves you a $400 motor, it's worth it.
You know, I like that idea. What you're saying is that I could have took my drum switch. I could have then lowered it, right? I could have, let's say, got in my boat, and if I had a limit switch on the bottom that once I said establish where I want the lift to drop to, then I wouldn't have to worry about trying to get up there, because that was our deal with the rope. Because you got down in the water, now I can't get to my drum switch, which is up high, so I had to put a rope on there, where I wouldn't have to do that. I can just get in there, hit the button, get in the boat, it's taking its time, and when it gets down to the bottom, the limit switch would have been normally open contact, right?
Normally closed.
Normally closed contact, right? Or whatever it's going to be, and then it would have opened the contact, and then it would have stopped the motor.
Right.
And if the motor didn't draw, I could have then not used the pilot duty, right, Dan? I would have gone with Dennis's. That would have been, because it was only like well, we have to see the horsepower of the motor, make sure to get the right limit switch, and then I could have done the opposite. When I raised the motor would have only gone up. So that was another thing. You had to stand there with the drum switch because you had to look to make sure that you didn't go too far, because the cables then would wrap all the way up and then it would jam. Then you'd go too far and then you could feel the torque. So limit switch would have been put on the top, so I could do what? Get the boat on there, turn it on, everything is looking good, it's solid. I can then get my gear cleaned up while the lift is coming up, and when it got to the top, the limit switch would have opened the contact or whatever the situation is going to be, and it would have stopped it. I like that.
Another good application is garage door opener. You're going to have limit switches on your garage door.
Good point. Garage door goes all the way to the bottom,
Yep.
and you adjust it to just the point that you want it to go to that spot, and you want it to raise up just to the point that it stops, that it doesn't end up
Right.
creating an effect like that. Great. I love this. Good stuff, guys. Thank you. Mechanical. Common applications. Oh, here we go. Limiting travel. We just talked about that. Automatic forward and reverse. Oh, we could make something with a limit switch that says that, hey, when this switch closes, and then we want to then change the direction or something, right? We could cause it to do something else than going forward. Starting and stopping magnetic starters, counting moving device. Every time it goes by, click, 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 click. Emergency stop, yeah, obvious. Initiating alarms. Hey, turn on alarm. Hey, something happened here. Double limit switch. I guess the other one was a single limit switch, and this is a double limit switch. Standard limit switches come with one set of normally open contacts and one set of normally closed contacts. Both sets of contacts are mechanically interlocked, so they both operate at the same time when the operating lever is activated. And there's our examples of volts and amps and class and type form. And what we'll do is we'll go ahead and get the limit switches that we have here, and we'll update this graphic to reflect those actual numbers. Limit switch proximity switches have no mechanical arms or levers and are able to detect the presence of nearby objects without any physical contact. They use magnetic fields or capacitance or inductive reactance to sense when objects come in close proximity and then open or close electrical contacts. Dan, I think you got a proximity switch there. Show us what you got in that
This is
one.
an example of a inductive proximity sense whenever metal.
Tell us about inductive. So now, if it's inductive, Eric, help me out here. Okay, let's talk about what it does, and then I want to understand the concept. Go ahead.
Well, when metal comes up here, it causes the contacts to change their state. Most proximity sensors are solid state, so they would only be used in class 1, circuits, control circuits.
So you say most proximate switches are what?
Have solid state components instead of actual relay contacts.
Solid state components. Okay, so it's electronic.
Yes.
Okay, all right, so it's electronic because it's using very, very low levels of energy.
Yes.
It can't, because it's only using inductive, what to say, there's metal there, and then we have we have an inductive field, and then it's able, okay, doesn't matter how it's being done. Okay, I got you, okay.
So this would be used to activate coils or pilot duty.
When
Equipment.
something was metal, in this case,
If it's inductive, it has to be metal.
but it has to be then a ferrous metal, something with iron content.
Yes.
Okay, I'm not going to get into how that whole thing works because it's not necessary, it's electronics. But didn't we have something optical here also? Oh, well, that would be a different one. No, proximity could be an optical sensor. Didn't we have another,
Yeah, you have slides on those. We have several optical.
no, that one is optical as well.
This one's an optical. It actually has a photo eye, a emitter on one side, and a receiver on the other side here. So as something breaks that beam, then it would see that.
Now that can also be solid state then, right?
Yes.
So, okay, and then I could count every time how many times something went past that point or whatever it is or when it lines up, as soon as it hits that line, it stops the process. There's a
Yes.
lot of different things I can do. I just know that, guess what? Something passed that given line. And now what I want to do with it is up to me. Isn't there another optical sensor that you have there?
Yeah, we have several. This is an example of what they call a proximity photoelectric sensor. This particular one emits, bounces off the object that it's going to detect, and then it sees the beam back to itself on a photodiode.
Would it be able to measure distance? Would it be able to say, okay, how far away that is from something? I guess they must make them that way.
They do make them. They make a laser that have a line camera, and it actually counts the pixel that it returns on. Most photo eyes work on what they call excess gain, which means that you adjust the strength of the signal that it outputs, and the distance that it is far away.
You
will
might want it
reflect
to
some
be
of
so
that.
far away, and you can adjust how far away before you sense, okay, that's the point that I want to stop it at.
Yes, exactly. So that it won't see background objects. This particular one is what they call a perfect prox. This one always has 100% excess gain, so it's always sending out as much energy as it can, but it has actually focused the emitter to the receiver, so it will only sense within a very minute distance.
Okay?
Because if you get too close, it'll shoot it away. If you're too far away.
Real quick, another type of proximity might be the loop underneath an intersection when you drive your car up to it. And it's just a simple way of, there's a loop which detects
Is that
the
an
ferromagnetic.
inductive? Is that using induction?
That's
Using the
inductive
car
proximity,
steel?
right. And that would be a good example of why we would study control circuits, because when the car drives up to it, then it's going to trigger the circuit to say, hey, there's a car here, turn the light on.
Anything else, guys, on that? All right, we're going to go on to our slides. And we already covered it, having to do with optical limit switches. And we just, Dan did a great job explaining all the different ones we had. Pressure switches. Pressure switches are used to monitor the pressure of liquids, gases, and vapors. Let's see how this works out. Okay, here's our normally open, normally closed contacts. We could probably put a couple wires inside here, and we could see, which way it's connected, so that if we get enough pressure from whatever the case may be, liquids or air, it's going to push this plunger up, and it's going to open these normally closed contacts to the point that it's going to then close these normally open contacts, and then we're using one set or the other for some application. That's all I got. Oh, here's the symbol, your pressure switch. You guys any comments on pressure switches? Steve?
One thing that doesn't really show in a symbol, whatever, we just show the contacts, but there's another part of a pressure switch that kind of goes unspoken. That is, there has to be a differential between the switching points.
What's that mean?
Meaning that you don't want to have it setting where when you get to a certain level of pressure and your contacts close and then your pressure drops back down just a half of a pound per square inch, it opens again. You've got to have a difference between, so you're not turning your compressor off and on continuously.
So we would have this on an air compressor. You would get up to a certain point. It would go down to a certain point. That means that when it gets down below a certain point, then the contacts would close.
Yeah,
it would
say-
start to compressor.
Say 30 pounds.
And then it's going to continue going up to, let's say, 100 pounds, and then it's going to
It'll
open. but there's a range saying, hey, well, don't turn it on until we get
At 99, you don't want to drop down to
we
99.
want to maybe go down. You have some
You can
control.
go back down to 30 again, or whatever your.
Now, I have a well, and
Yeah,
I have a
same
baffle.
thing. Yeah.
So the key is my motor starts when I get below, let's say, 30 pounds of pressure, let's say, or 20 pounds of pressure, and then it fills up the baffle to 40 pounds of pressure, and then I can still take the shower, and I can turn on I can flush the toilet and not have the motor go on and the well every single time.
Right.
So what would that be called? That would
It's
be
a differential.
a differential.
Usually there's a differential adjustment on
Now, my
on-
well, the differential adjustment, I can't physically see, but what I can do is I can turn the hose open and I can see when it comes on, and then I can see when it stops. And I can adjust it with like a quarter, I think it was a quarter drive or 3/8 inch drive. And then I can see, okay, it starts sooner or later, and I can change that range.
Yeah, you're kind of adjusting the tension on that spring, probably, I think is what you're doing.
Got it. All right, we'll move on. Next one is going to be some common applications: air compressors, well pumps, man, hydraulic systems. There's just unlimited number of applications for pressure switches. A vacuum switch, another type of pressure switch. Instead of pressure, there's a vacuum chamber. Some vacuum switches are manufactured. They can serve either function. A vacuum. How would that work? Is that where it goes the opposite direction, right? So if the pressure goes down, how does the vacuum work? Oh, this is a vacuum chamber. Anybody have any experience with vacuum at all? Dan? Tell us about vacuum.
The diaphragm would pull down, and your normally closed contacts would actually open. And
Okay, so what it's going to do is it's going to go down where if it's going to be pressure, where it's going to be going up, where the vacuum is, okay, it's going in the opposite direction. Pressure is going in that direction. Okay.
Yeah, normally they're a large diaphragm. You have a fitting on either side of the diaphragm, so that normally can either be used for vacuum or for pressure, or if you connect both lines, they can do differential pressure, which you might need, like if you were wanting to know when your air conditioner filter was dirty, you could put one on either side of it and have a setting to where when your air conditioner filter was dirty,
When it
would
got too much
actually
pressure, the
turn on
differential.
a light, yes.
Excellent. Let's take a look at the symbol. So this is a vacuum. What's the difference between that and a pressure? Okay, so there's no difference you'd have to know the application. All right, let's move on. The setting of the spring, which Steve, I think you mentioned it, determines what pressure the electrical contacts change state. There's often a setting to adjust the differential between the switching points. Push buttons. Push buttons, they're switches that are pushed to make or break contact rather than move a handle. Now, be aware that this is your momentary contacts normally open, right here, here's the symbol, and then we have normally contacts that are normally closed, momentary contacts that are normally closed. And Dennis, you got a couple of switches there, and let's take a look at those. Let me see, are they red and
One's
green?
red and one's green.
Now, both of those red and green, are they both identical switches in the sense that they're normally open, normally closed, and that red is just something? Where
Yeah,
do you get red?
this comes out, this pops out right here. It's just a little disc,
Okay.
and then it just pops out.
Do you have some of these that are illuminated under normal conditions?
Yes, you could have some of these that are.
So that'd be a
illuminated,
separate
right.
little power for that there.
And then typically they're going to come with, one's going to be normally
Let's see if we
open,
can
the
zoom
other
in a
one's
little
gonna be
closer on that.
normally closed.
Okay.
Okay, and all it's got in there is a spring, and so when you push it down, it just goes the opposite direction.
Okay, that's a momentary, normally closed, a momentary close and a momentary open.
Right. Right now, it's in the de-energized state.
Right.
So when I push it, the normally open goes closed, and the normally closed goes open.
Got it. All right, we'll move on. Pretty simple, straightforward. Push buttons. A single push button switch can have additional sets of momentary contacts. Let's take a look at this. And that's what we just showed, what you just explained, Dennis. Normally close, when you push it, will go to open, and then the normally open would end up going to close. Or the symbol could be just simply like this here, showing you a momentary push button. There's a set of normally closed contacts and a set of normally open contacts. Now, we've been showing the NC, NO, and we haven't described it, but I think people have picked it up, normally closed and normally open. In reality, on the diagrams, do they tell you that it's normally open or normally closed? Or when you look at the diagram, you can see it's a de-energized state, and you can see that this is already closed, and this is already open, so that means this is a normally closed button, and this is already normally open. Is that the way it's shown?
That's correct.
Okay. And here, oh, Dennis, looking at your switch, does it tell you which one is, does it show you a symbol of the normally open, normally closed, or does it tell you that's normally closed, normally open? How do you know on the 4 screws?
Well, it's got the normally closed is up on top here.
It shows a symbol of it?
Yeah, it shows a symbol with the regular contact, and then it's just got a slash line through it, so it's normally closed.
Got it. There are many other push button configurations. Some have larger mushroom heads and are illuminated buttons. So here's a symbol of a mushroom head. This is normally open, momentary close, normally close, momentary open, and then you get illuminated. And you press the illuminated button, and we'll talk about that. But that's normally closed, momentary open, normally open, momentary close. And Steve, I think you got a...
Yeah, I've got one with a mushroom head on it. And those heads, this particular one comes with either the mushroom or just a standard head, and you just interchange them with an Allen wrench.
I was just going to say, how do you get, so you just
Yeah,
get a
there's-
regular,
there's
the
an
one that
Allen
Dennis
screw.
had showed us, you just would get the mushroom head, you just kind of get it on there.
Well, it came with the switch, but the switch is just versatile where you could use it either with or without this mushroom head. I can just take these screws out. Back
Now, you
off a
know, the
little
National
bit,
Code sometimes,
and you can change the heads on that one. It's just got
different
set
colors,
screws.
different configurations.
Yeah, and a lot of these others, here's another one that comes with different heads, different color heads. So you can use them or you can use the red head, depending if you're using it for a stop or a start.
Got it. All right, let's go on. Continue on push buttons here. This is a push button station. It's an enclosure that contains a combination of push buttons. You know, whatever. And of course, you can get legends, and you can get plates and marked and engraved and whatever else you want there. What do you got there, Steve? What's that
I've
one?
got one here that is just one button, one situation. It has both buttons, both a start and a stop in the same
Okay,
in
there's
the
your
same
station right there.
device. Like
Okay. Solenoid. Let's talk about some solenoids. It's an electromagnetic with a movable plunger. When the coil is energized, the magnetic field pulls the plunger in. We talked about this a little earlier, and when it's de-energized, the plunger then moves back to its original position. All right, here is a solenoid symbol. Right now it's de-energized. If I energize it, it's going to pull the plunger in. Here's an example of a solenoid. This is often used for sprinklers that, you run your 2-wire control wire here, like in my house has sprinklers. Well, then you run 2 wires to this solenoid. You energize the coil. That magnetic field draws in this armature or this plunger, and the result is that it opens up the water flow, and they continue on, and liquids move for whatever the process that you want to move for. Toggle switches. Manually operated devices. Kind of straightforward. Just turn a switch on. Well, what does that look like? Well, it has a switch like this. Now, we're going to talk about these abbreviations, which was discussed in the abbreviations unit. I think that was unit 2 that we didn't talk about. And this would be a single pole, which means there's only one line, and it's single throw, meaning you either open it or you close it. So your switch at your house that you turn on your lights is going to be a single pole switch, because it doesn't have, it's not 240, it's just 110 in this case. And it either goes on or it's off. So it's single pole, single throw. Okay, got that one. Here is a single pole, meaning, one hot wire. Double throw, which means you could have it on load B, or you could switch it and go to load A. It's double throw. It can go one of 2 directions. Eric?
Also, it's very typical for that contact to be described as a Form C contact.
Form C.
Form C. A Form A contact is a normally open, like you showed on the previous slide. That would be considered a Form A. And on lots of literature, you won't see NO, you'll see A. You'll have an A contact.
Well, you know, I don't know where the A came from, but I can see where that could be looking like an A, right? And I can see where this looks like, I can see this looks like a C. I can visualize how this looks like a C. So at least there's a little bit of logic if that is the logic.
Well, to continue, Mike Culbreth has gotten some of his graphics and some of his limit switches and things. He'll have a normally open and then a normally closed.
Right.
Okay, well, a normally open is a form A, a normally closed is a form B. Oh. But sometimes when the normally open and the normally closed are together with the same armature, then it's a form C.
Okay. All right, let's look back here. This is a three-way switch, right? Single pole, double throw. So it's a three-way switch where you can go from this point here, you can supply load B, or switch it up and supply load A. I don't want to get any more detail, I think, right now on that. But I guess I am. This is a three-way switch, which is a single pole, double throw. Let's go back here. Single pole, one line, and it can go up and down, so it's double throw, SP, DT. And if you put a single pole, double throw on the power coming in, and then you put a single pole, double throw supplying to the load, you can use two three-ways. And by the way, single pole, double throw is a three-way switch that you can control one load from two different locations. Let's take a look at this. Line one comes in. The switch, in this case, is closed at this point. Power goes over here and it stops. The load is not operating. Take the first switch and go to the other position, the other throw, up. So now it takes power, goes up to the top portion of the first three-way. Then it goes over to that three-way that was already in that position, supplies a load. So that means you can turn the load on and off by going to switch 1, three-way. Now, back to our state again. If I take that switch on switch 1, leave it where it was, which was on, or it was up, go to switch 2 and turn that switch the opposite direction, the load goes off. Then I could go back to switch 1, since it was already in the up position. I could switch it down. It would then turn the load on. Eric?
It might be beneficial to note that in a single pole double throw, the double throw refers to the number of on positions.
Hold on, slow this down. The double throw refers to the number of on. I love it. The way you think, Eric, it's always brilliant and it's fascinating to me. The number of on positions.
Right,
Double
because
throw. You could throw it on here. Okay, I got it.
Because you also have a single pole double throw center off. You either have a switch which is on, or you have a middle position of off, and you can go either way.
And that would be called single pole, double throw. Well,
center off.
Center off. Okay. Let's go on the next one. We're now moving to continuing symbols for switches. We're just talking about symbols, not how the stuff works necessarily. This is going to be double pole. That means, here we go, line 1, line 2, and then we're supplying the load 1, load 2, double pole, and it's a single throw, and that's a number of on, and there's only one on, so it's a single throw. Got it? Here's a double pole, double throw. So I have two poles, line 1 and line 2. I have the on up, and it's a double throw because I can throw it down. Now that's one method, double pole, double throw, single break. Then you could have a double pole, double throw, but it's double break, where I'd press 1 and 2 would be contact, and 5 and 6 is contact, but if I press the button, this shows a mechanical connection, that if I press this button here down, it opens 1 and 2, closes 3 and 4, it opens 5 and 6 mechanically, and it closes 7 and 8. Help me, guys. Why would I use one versus the other? Is there a reason to have a double break versus a single break?
Well, one reason, Mike, to have a double break contact is for higher current flows. If you just have a single break, then your current has to be broken on a single contact.
Hold on. If I have a single break up here, you're saying when I push this button, I'm breaking all the energy on a single
Right.
point, and I'm making then, if we show the next symbol, I'm making it all in one point.
Right.
But if I do a double break, the contacts are going to be open at two locations. The energy of the arcing is going to be at two locations. And when I make the contact on 3 and 4 in this example here, then I'm distributing that arcing, that making the contact at two locations.
Right.
Really? Well, would this then have to do with the rating of the switch? I
Yes.
mean, so if I buy a switch that's a single break, it rates so many amps. But then if I buy a double break, it rates more amps. Right? It's rated for a higher ampere rating.
Right.
Dan, you're giving me I don't know about that whole story there, Mike.
Well, why
think-
we normally use them, if you have a double pole, double throw, would be so that you can separate the two circuits more than, so that you would have a normally open and then you could use the normally closed in another location in the circuit.
Okay, what you're saying is that this allows me to have two separate circuits.
Yes.
That I want this one to open, which is a separate circuit to open, and I want this circuit to close, and they might be off of different power supplies, maybe different even anything.
Like when you were talked earlier about the limit switches, if you had a limit switch to change direction, like on a knife grinder that would go back and forth, sharpening the knife on a grinding wheel, that your limit switch could break one circuit to cause the travel in one direction to stop, and then also start it in the other direction.
Okay, so there might be different applications.
Yeah.
So there might be ampere ratings. Hey, listen, I don't want to have just one circuit controlling up or down. I want to have maybe two different things, one to close in this case and then to open this case. Okay, gives you more devices or more control or more make and break contacts in the single device. Steve?
Yeah, then if you're going to use your symbol in B up here, in the same way that you use A, you're going to have to put in a jumper between 1 and 3 and between 5 and 7 to make it actually duplicate that.
You're saying, Mike, if you want to have one come in and make it a double throw, then you would put a jumper between 1
and 3
and 3.
and between 5 and 7.
Let's see, a jumper 1 to 3?
Yeah.
And a jumper, oh, I see what you're saying, yeah, but then the numbers aren't related here. You're just
Right.
basically saying these are connected to 1,
Yeah.
right? And you can normally close, normally open.
Right.
And 5 and 7, you can jumper it. So you can get this effect
Yeah.
by putting a jumper across these.
Right.
You know what I'm picking up here? Is that once you learn how this stuff works and how it kind of connects, you really have to be knowledgeable in product. You got to know what is available. Because you're saying, I want to achieve this. Well, in order to achieve that, then you have to understand that they must make devices that are proximity switches with inductions or capacitance or optic or that it makes us break this one. So you design what you want, then you're going to have to go out and find somebody that makes those type of devices, right?
Well, and the other thing about that also is the fact that all of a sudden you may have to be troubleshooting something, and like we were talking yesterday, Eric and myself, was that, you know, on a plant, if it goes down, it could be $1 million a day downtime. So just because of one little part like that, you need to understand how that thing functions so that you can replace something that broke so you can get something back up online.
Like Steve said, you can rewire this, put a jumper here. In other words, something,
Exactly.
because you know how it works. Now, Eric, at lunchtime, you were saying that some of these switches don't necessarily make it real clear exactly how it works, and that you'd have to get a continuity tester.
Yes, Mike, on the back of this switch, which is not made in the United States, but regardless, you have 4 different symbols, 2 normally open, 2 normally closed, and by looking at the back, it's not necessarily obvious which one goes to which. Looking at the side, it becomes a little bit more apparent, but you can't, there's no plexiglass, you can't see the contacts, and so sometimes, even if you've been in the business for quite a while, it can take a bit. It can take a bit of looking and analyzing just to see which contact is which.
You might have to get an ohm meter, just say, oh, okay, there's the close, here's the open.
Right.
And not, okay. Thank you. All right, let's go on to the double pole, double throw. And the double pole, double throw, would be what we would call in the field a four-way switch, where in one setting it would go from this point to this point, and then if you switch it, the double pole, double throw, this one then switches down and switches up. I'm not going to get into too much of this, but let's just describe this. Here's your three-way switch in the beginning. Here's a three-way switch at the end. Here's your four-way switch in between. Right now, this switch setting, the way it's set, there is no power to that given load. All I have to do is take any one of these three switches, either the three-way, the four-way, or the other three-way, and change the switching. In this case here, we're switching the double pole, double throw. That changes, the power goes in, goes up, over, and supplies the load. Dennis.
Mike, I think at this time, I mean, if you look at this, you know, the typical residential wireman, even a commercial wireman is looking at this and going, you know, now this is really starting to make sense because for the simple reason, you know, the load is a light bulb.
Right.
And now we're taking it back to the basics and saying, this is all it's about is motor controls is you can use switches for motor controls. So to me, this really helps, you know, a typical
if
person.
all our switching done was mechanical, you close this one and then you open this one, and you open this one, you close this one. I mean, if it was all done mechanical, then the guys wouldn't have any problem following
Right.
that. You'd have all these switches all over the place. Okay, close this one, okay, and open this. But the problem is it's put in these in containers, and it's done electronically, and then it's into computers and programmable logic controllers that it's to get further and further away, that you got to be able to visualize this and have that concept of what is really happening out there. All right, let's move on to a non-fusible disconnect, also called a safety switch. This type of switch can be used as a manual on-off disconnect and incorporates the use of pivoting knife blade type contact points that operate from a handle. Just your regular standard old disconnect. And here's your symbols: double pole, single throw. This is three pole, ABC, line 1, 2, 3, single throw. And this shows that they're mechanically connected together. That's your handle, which is right there. Those are your blades, making contacts right here. And so what is three phase, a single phase, three phase, doesn't matter. Here's the symbol. Fusible disconnect, kind of like a no-brainer. The difference is you just add fuses to the disconnect. Here's your knife blades. Here are your fuses. Single pole or single phase and three phase. Temperature switch. This type of switch has a sensing bulb with a capillary tube connecting it to a chemically filled bellow. Eric, you know all about words. Is that supposed to be a bellow or bellows?
Bellows.
Why? Oh, no, I'm not going to go there. Fine. So here is a temperature switch. Let's see how this works out. Now, this is a sensing bulb, and I guess it will then let us know. And then we think, now, could this be used? I guess it could be on-off, a regular thermostat, right? However it's going to work. We could probably show a picture of a thermostat in there also. Might not have wouldn't have a capillary tube, but I mean, it could just be a make and break based upon a bimetal. Here is a symbol. Do you guys have much experience with temperature sensing? Do you guys, Dan, you guys use any of that at all? Is that?
Yeah, we use a lot of temperature sensing.
Are you sensing a specific degree that you can put in a computer and it says what the temperature is in that particular location? Or are you saying when it gets to a certain temperature, then start a process or end the process? Or what's the applications that you use it at?
Normally, these type you would use to sense either something's too hot or something's too cold. A lot of our control, of course, is analog, which means that we sense a variable temperature and can control based on that.
So
But
you would know
to
what the
be on,
temperature.
off.
So with a computer tying your equipment, you would know what the temperature actually is at that given point, and then based upon that information, you could take action.
Yes.
Eric, what about you guys on Dow Chemical?
Same thing. We have analog measurements to where we will, a temperature element, for example, will be a RTD, which goes to a transmitter. It's all electronic, in other words, instead of the mechanical bellows and the contact switch, but the principle's identical.
All right, let's move on. Timing relay. Pneumatic. When the relay is energized, the solenoid plunger is pulled up, air enters through a needle valve, and slowly fills the bellows. When the bellow air chamber is filled, one or more sets of contacts are activated. Modern timers are usually solid state. All right, let's take a look at this one here. So this looks like it had to be like old school stuff, that you put a coil, you energize this coil, and it starts to try to do something with the armature, and of course there's air in there, and then, you know, we have a valve in there that allows the air to kind of slowly leak out, and as the air displaces itself, then it can then make and break the contacts. So it's a timing device, and so here's your adjustment as to say, well, how much air are we letting allow to release determines how fast that contact is going to close or open in that case. Is that like old school? Do we still use this, or is it more done electronically? That is a timing, electronic timing device. You got something?
Nowadays, normally you use electronic timer. Those were real popular because you could use an off delay, which is hard to do. You used to have to use 2 delays to keep something on after you've turned it off for a short period of time. The problem with those, especially in a mill condition, is you have a lot of dust and you actually have a spring in the bellows pushing against a needle valve, and very, very precise. Well, you get a little dust in there and you're not precise anymore, so the timing could vary considerably.
Steve, show us the one that you have your timing relay. Now, what are the choices, Steve, on that timing relay? What were the choices that you had? I see there's some adjustments.
Yeah, there's adjustments. This one has both an on delay and an off delay, so you've got both those incorporated in the same timer. And then you've got the amount of on time you can adjust, the amount of off time. And then there's a selection of ranges. You can change the range so it'll time anywhere from 0.6 seconds up to 24 hours.
So that's pretty cool. I like that. And here's the symbol right there. Here's a normally open time close. Normally close time open. And the energized arrow is on time delay. Down arrow is on delay is the arrow up. And now down arrow is on delay, off delay. All right. Now, I think we're kind of like finished up symbols as much as we're going to work with. And this is just kind of showing us a ladder diagram. You can see how we have one line across here and have second line there, and there it gives us our nice ladder. And this is a momentary push button that's normally closed, right? Mm-hmm. This is a momentary push button that's normally open. This is going to be a coil that's identified as coil M. Here's a light. We didn't talk about the light symbol, but that's a light symbol with the little dashed lines out there. So there's no standard color, but probably R is going to be red. And control wiring is a small wire, so that shows as a small wire. That's control wire. The power conductors are bolder. This shows a wire connection. We're making a connection here, making a connection there. There's a connection made there, another connection there, another connection there, a connection there and there. The numbers. Terminals 1, 2, 3, 4. They might just be used for convenience. We got the pilot light. We got, fuses. We didn't show the symbol of a fuse, but that's a symbol of a fuse. We discussed it previously. And, okay, contacts. Here, since we're showing this, as Dennis mentioned, in a de-energized condition, these contacts are open, so they're normally open contacts, and these contacts are closed, which means they're normally closed. And I'm not going to talk about how this circuit operates at this given time. Yes, Steve?
We had some discussions among us off the video about the numbering. And this is a real standard type of numbering you'll see where there's multiple contacts controlled by that M coil, and we number them M1, M2, and so on. But when you get a real complicated diagram where you have multiple motors, your starters are numbered maybe M1, M2, M3, and then the contacts might be an M1A, M1B, and so on. So just the student should be aware that your numbering is not a universal thing, that can vary with the situation, with the blueprint you're working with. You just have to really stay within the context of what the manufacturer or the engineer give you.
Well, you do run out of 1, 2, and 3, and 4 pretty quick. You know?
Yeah.
Once you use it once. Okay, well, 1, 2, and 3 are being used. Okay, motor 2.
Yeah.
We need to start coming up with some numbers. And then the A maybe capital A, maybe a lowercase a, you know, you start doing ways of breaking this thing down. All right, that is the end of chapter 1. We are now beginning chapter 2. Let's see what this is talking about. Basic concepts, components, schematics, and motor control circuits. Unit 4, components of control circuit schematics. To work on motor controls properly, you must become familiar with motor control schematics and diagrams. Now we've talked about what a ladder, what a wiring, pictorial, now symbols. Now we're going to start putting it together. Let's take a look at a simple control circuit. Using a ladder diagram, we have line 1 connection going to a single pole, single throw switch, going into another symbol called overloads, which we haven't discussed yet, but it's a normally closed contact either way, going physically to a motor. So this motor is actually operating at line voltage. Not a control circuit, so probably, I guess we can leave that wire. I'm not sure. Should this wire be a bolder line, you think, or should it be a narrow line here? Because we're not using control. It's a control, but we're using line.
We're switching the power.
We're switching.
Switching the power.
We're
That's a
switching the
manual
power.
motor starter of sorts. You would probably want the bigger line.
Yeah, I think we're going to go with the bigger line on that one there. Not the big deal for now. Okay, now let's correlate. What does that mean? Well, your single pole, single throw switch is your toggle switch here. The overloads, which we'll talk about another time, not right now, is contained in this actual manual motor switch with an overload. And then here's the pictorial of that motor, and then it connects over to the neutral. So here's your ladder diagram of what pictorially is being displayed down here. Okay, Steve, you got a...
I've got a little manual motor starter switch here. One, it shows how it comes in the enclosure if you buy that whole enclosure. And then here on the other side is just the switch outside the enclosure, and you can see the overloads right here, the heater.
Turn it sideways. I want to see what's the side. Show me where the line 1 comes in. Where's the line 1 come in? Where's the hot wire come in?
Get my eyes on this. The hot wire on this one looks like it would come in up here, and then the load side comes out down here.
Okay, so it actually is
feed through
going.
that overload.
It's a little different than what we'll show on the graphic here. We'll change that. So it really is. Right now, yours is coming in here.
Yeah, and
it's
different
somehow-
manufacturers could lay that.
Okay. And so that would be an example of a heater on the side, overload,
Over here.
right there in that graphic. And that is what is demonstrating here. And that is a symbol for an overload, which we haven't discussed yet, but now's a good time to pick it up. And I'd love to talk about what the overload does, but I'm not going to do that right now. We're just going to try to show you a simple control circuit. All right, let's see how this thing operates. Single pole switch, there's an overload. The overload is normally closed. We're supplying power conductors, so we'll have all these conductors, you know, the standard size. And over here, I close that switch. We'll then power, oh, 1 second. The neutral's connected to this side of the motor. The hot wire stops over here. Close the switch. Power continues to the motor. Motor operates. If for some reason the overload operated, and Steve, show them where that overload is, and we'll have Gary zoom in on that, right on the side there, that if for some reason over time something happened that caused, is that like a bimetal that it opens, Steve, if it gets kind of warm? Is that, you think?
This one's a melting pot alloy.
So it melts.
I doubt if you can zoom
We'll talk about those.
Yeah.
Whatever it is, it opens that circuit.
Right.
Right there.
It uses the heat principle. It just heats up some solder, and that solder is currently holding the contacts closed because it's keeping a wheel from pivoting. There's a spring-loaded wheel.
Okay.
And when that solder melts, it just simply allows that wheel to move. The shaft will the shaft is embedded in the solder.
Is there a reset button on that?
Yes. Well.
Or is it automatically, I guess, close
this one.
as it cools down, it just kind of resets itself?
Yeah, this, I don't see where the reset is on the manual one, because it's the same principle. It's going to have to cool down, and you're going to have to
switch.
Yeah, oh, yeah. On this one, it's probably a switching mechanism when you turn it off, just like resetting a circuit breaker.
Ah, good point. Internally.
There's a mechanical
Now,
link in
does
there.
it have
that
an
I can't
ampere
see.
and a voltage rating on that switch?
This one is, 1 horsepower rated, and it's 115 through 277.
Okay, so it's a 1 horsepower motor rated switch with an overload. That if it heats up, then the overload is already set normally closed. But if that motor was drawing more than the ampere rating of that switch, then that overload would open and protect the motor from failure. All right, adding an automatic control device. Let's start reading some of these schematics. All right, so we have our switch and we had our overload, our manual switch we had right here. And we decided we want to add a float switch. So I could turn this thing on, but I only want the motor to run under the condition, in this case, using the normally open float switch. I only want the motor to kick in the event that the liquids rose up to a certain level. This would be very common as a float switch, a sump pump assembly in a basement. Steve, you live in Oregon area, or is it Oregon? I know these guys in Oregon are very sensitive how I say Oregon. I've gotten that before. Am I right about it? It's Oregon? Oh, that doesn't matter.
It's
then.
either way, Oregon, Oregon.
Okay. All right. Wherever you're at, do you have a basement in your home?
I don't, but it's very common. And yes, that's
Anybody here have a basement? Steve, you got a basement? Now, isn't it flooding right now in North Dakota? You live in South Dakota?
I'm in South Dakota, so we're not flooding, but I have a basement that is in an area with soil conditions where it is apt to, and I have 3 sump pumps.
You have 3 sump pumps. Wow. Okay. Do you have the kind of float switch that we're showing here? What does your float switch look like?
I have a couple of different ones, but one is very similar to that. It's integral to the pump. This is just showing the switch mechanism separate. It's integral to the pump, though.
Oh, so the pump itself would
It's
be
a
sitting in there.
submersible pump. You drop it down in there.
You know what? That's just like my boat. I have a boat, right? I have an automatic pump that when the, whatever you call it, inside the boat fills up.
Pit.
bilge.
Bilge in a boat, huh?
Okay, oh, it's a bilge. That's why they called it a bilge pump. I didn't know that. Okay, so anyways, in my bilge, when the water level comes up, it raises the float and it turns on the motor. So that sump pump float is actually built within the motor assembly. Take us a couple pictures of the different ones and send them to Mike, and then maybe we can add it to the book. All right. Any other comments on?
And again, there has to be a differential on those kind of mechanisms too.
Why would you have a different?
So that the pump won't be running continuously.
What do you mean by differential? Because if it goes
So
up, it turns
your
it
float
on.
has to go up to turn it on, and then you don't want it to turn on again. I'm sorry, it has
I see what
to
you're saying.
go down to shut it off, and then as soon as the first cup full of water comes in, you don't want it to turn on.
You don't want it to be
away.
taking out. All right, it goes on, it starts pumping it, and then it stops. When it stops, it then takes a little bit of water that was still in the hose back down, just enough to cause it to go
And
back
you don't
up
want that
again,
to
and then
happen.
be going back and forth and back and forth.
Yeah, so you've got a level. You want it to come up to a certain level before it turns on, and then when it pumps out, it'll go below that level to shut off.
Got it.
Your graphic actually shows those little set collars, and you can set those to actually change the function of
Aha. I knew that. All right, next one. Let's take a look about adding this control device, this automatic control device, to our existing circuit. Single pole switch, normally open. Overloads, contacts are closed. Float switch is normally open. Motor is not running. I decide I want this thing to work. I close my switch. Overloads are not open. There's no water. Power stops at this location here. There's a neutral on both sides, and the motor's connected with the neutral. Nothing happens. Time goes by, whatever reason, moisture, liquids enter, closes the float switch. Since my single pole, single throw switch is closed, overloads are closed. We now close the contacts for the float switch. Motor kicks on. Hey, guys, we're reading control circuits now. Pretty cool, huh? Ladder diagrams. All right, let's take a look at the pictorial of this. Here is a single pole switch, single throw. Power goes over to, we don't see it here, but power goes over to a set of contacts. I see what it is. Okay, power comes in. So this is just a switch in series with this switch. That if this switch is closed and it goes down, and if this switch is closed, then power comes back up to the switch leg, using electrician's term, and then of course the neutral is directly to the motor. Am I right, guys? So now, because it's series for the current to flow, both switches would have to be closed for us to be able to have this. We have two conditions. One condition is you got to turn on the switch. Second condition is the float has to be activated to close the contact. If the float is active to close the contact, but the switch is off, since the switches are in series, nothing happens. Eric?
And the third condition is the overloads have to be closed.
And the third, okay, because we have the switch, then we go to the overloads in series, then we go down to the contacts to sense whether the liquid has risen to a level, then we go to the motor. You know, and if something doesn't work right, by having the concept of like, well, all right, well, what's the voltage between the case and the line side of that switch? It should be what? Using, let's say it's a 120 volt circuit. If we were going to troubleshoot it, if it wasn't working, let's go to troubleshooting now. Well, voltmeter from the equipment case to the line side of the switch would be 120.
volt.
If I turn the switch off, the voltmeter here should be
0.
0. If I turn the switch on, it should be
120.
120. All right, so we got the 120. We know the switch is good. I then take the cover off of the float switch. Voltage is 120 here. The black wire terminating on one terminal. I just double check that. That should be 120. Turn the switch on or off. Okay, got that. Then go to the load side. It should be 0 if the contact is open. Then just kind of put my hand there. Is that right? Just kind of move this guy up and down to find out, okay, well, am I getting 120 on that contact? Yes, I am. Okay, well, then I come along here, then get over to this motor lead, and then make sure the switch is on. Make sure the voltage here, which means the overloads are good. Make sure the voltage is on the line coming in, the load going out, that's good. Come over to the motor, take the cover off, make sure it's 120. Hey, got 120? In my personal opinion as an electrician, I'm done. Goodbye. See you later. You got your voltage. Call somebody to replace your motor. You know, but you got the power there. So you can see how we're slowly building. And let's take a look back here. Here is the ladder diagram of that, right there, what we just did. So we're putting it together. I like this. Anybody have a comment on that before I move on?
Just as a note,
Yeah?
the way you describe that, your switch has to be on and the float has to be made and the relay. Anytime you use the word and, it's basically going to signify that those devices are in series.
And is in series, and I guess you're going to tell me or
Would be in parallel.
will be in parallel. I like
And
that.
if you keep that in the back of your head while you're writing out these relay ladder diagrams.
So you're saying to me now, you're talking at the level if you're going to be going in a programmable controller, right? You're using, that's the logic then. Is there an and,
well,
and an or?
that's a basic Boolean algebraic functions, but it can help you in hardwired circuits also, because just as we described here, you know, the three devices all.
So let's try
had to be
this.
on.
I'm going to try to work the word. Okay, this motor should run if the switch is closed and if the overloads are not open and if the float switch has risen to a level that closes the contact. Then you would have voltage to the motor. Let's put it that way. Not that the motor's running, but then you'd have voltage to the motor.
Yes.
And Eric, you said that we could put a flow switch in this motor, right? And with a flow switch, we could then determine whether or not the motor is actually pumping any fluids.
Right.
And if the switch is closed and the overloads remain closed, and if the contacts for the flow switch are closed, then the motor should be running. Then we need to make sure we have liquids. And if we don't have liquids, then we can have something else to say through some other computer control or something like that, saying, well, then turn off the motor. If we wanted to protect the motor against, let's say, a lack of movement.
Or we could use the normally closed contact and turn on a pilot light.
Oh,
or an
you're
alarm
saying,
at that point.
You're saying I could add a flow switch here with a normally open contact that if it flows, then the green light come on. We could, you know.
Yeah.
And if it doesn't flow, well, then the normally closed contact would be closed, then the red light would be on. So I
Yes.
could tell whether or not there's any liquid moving just simply because I can see the lights on. And the red light would be on as long as that normally closed contact that's in the flow switch here. But the green light can only come on if the green light bulb is good. and if we're having flow, and if we have voltage and what have you. Then we can even put another light saying, do we have voltage? Right? You can have a light that just says white. Okay, is there even any power for this signaling circuit? Okay, we got white. Well, then if we have white, then we might have a red condition or a green condition. So you can you can see this thing can build up. What do you want to know? How much money do you want to spend? How important is it to you to know this device? Or take that information. Well, if green comes on, then we want this condition. If red comes on, then we want that condition. So we're building. All right, control devices with multiple contacts. Most switching devices come with at least 2 sets of contacts. Here's a float switch. A float switch with normally closed sets of contacts, normally open, which means we could use it in that same circuit. If you close a switch and the contacts are closed, which means there's no liquid in there, then if you close the switch, the motor runs and it fills in this, let's say this tank, and once it fills it sufficient, then it would rise this lever and it would then open the contact and stop it. Dan, show us that device that would do that, where as it rose, it would then open a contact.
That would be in this configuration when the
So the contacts are closed, and then
contacts are closed, and as the liquid level would rise, then you would open your contact.
Got it. Now, we could take the same device, because it comes with normally closed and normally open contacts, flip it the other direction, that if I close this switch, well, then the motor's not going to run. But if liquids happen to can enter to some point, then we would stop it, or rather, we would close the contact, and then we'd activate the motor. So show us that one. So the liquid, the contacts are open.
That would be an example of pumping out of a vessel or a container.
No.
Or if you had water, it would pump until it's too low. Or, as you were alluding to.
Okay, right now that's open, right?
Yes.
So, but if liquids rose,
So if liquid rises,
it then is going to activate close the contacts, and it's going to do whatever we choose it to react. In this case, it's going to be closing, we're showing pilot circuitry, but we're showing really line power going here.
Yes.
So we'll probably have to make sure these wires are full-size conductors. All right, that's good enough. I think the point is contacts come normally closed and normally open. You know, there's a point that I see, I won't say I'm getting confused on, but I can see you have to be aware of, that sometimes you're making and breaking your power conductors because we're having power. And sometimes, which we haven't really got to too much yet, you're making and breaking control. Right now, we're just talking about logic. We're talking about making and breaking contacts. And so far, we've been talking about power switching, not control circuits, even though you're showing some kind of control devices. All right, that takes care of Unit 4. Now we're into Unit 5, magnetic control. That was all like manual control. Now we're going to get into some real controls. This unit introduces the concept of magnetic remote control devices used with both motors and other types of loads such as lighting. Electromagnetic control. When installed as a component in a motor starter, the energized coil magnetically pulls in a plunger with movable contacts that make contact with matching contacts from the power circuit or the supply circuit. My assumption is that you've taken an electrical theory course, you understand how currents travel, you understand electromagnetic fields, you understand a coil, that it's going to draw in an armature or it's going to push an armature out depending upon the configuration. So let's take a look at this graphic. All right, we have line 1 coming in, and then we have T1 going out to the load. That's, I don't know why T, I don't even know why line, but it's what we call it. And then we have a contact, and it's open. So right now, it's a contact that's open, and then we have some kind of control wires that would be connecting right here. We probably should identify this as the control conductors right here. So we have control wire. Let's say this was a 24-volt coil. If this were a 24-volt coil and we applied 24 volts to the coil, then we would energize this coil. It would create a magnetic field, and in this case here, that armature, which is what moves back and forth, the armature would be pushed in, and that would then close the contacts between line 1, making power continue on to terminal 1. Now that's just showing one contact. So here's line 1. Let's go back here. That's your line 1, nice and black. So it comes in. Internally, it's open, and then we go to terminal loads, and that would be T1. If we energize this coil, it then closes those contacts internally, and we have power. Let's take a look at it in this picture. That's the three-phase contactor right there. Here's, let's say, your coil terminals, which would be your control wires. Let's say we're 24-volt control, or 120 or 480, whatever you want it to be, 277. That if you energize this coil, it will take this armature magnetically, and it will push it, this device, or push in this direction. When it does that, line 1 connects to terminal 2. Line 1 now goes to terminal 1, rather, I'm sorry. Line 2 makes contact to terminal 2. So then line 2, contact goes to terminal 2. Line 3 will come across there to terminal 3. Line 3 goes to terminal 3. Anything you guys have here special that you want to say? So that's how a magnetic contactor works. You know, one of the words that, I'll wait, I'll say it now and I want to say it again a little bit. One of the words that always bothered me is like when you call it a contactor and you call it a starter. Steve?
I was just going to say on this type of frame that you have on the screen here, you want to be careful what position you mount it in, because if you mounted it upside down on some of them, they wouldn't open. It has to require the springs to come open and so on. So the mounting position is important. We can't.
So you're saying I might take a contactor and not be aware of this, and I mount it, let's say, on
Upside
top
down.
of something, and the gravity might close those contacts.
Yes.
Steve, what do you got there, Dennis?
Well, it's the contactor, you know, and basically what we're saying, what I think Steve's saying is holding it like this instead of mounting it something like this.
Yeah, you got to look at what position you're
You
putting
know.
it in, because some of them require spring or gravity to open.
Right.
Is there a button that you can push those contacts in? I mean, can you push the contacts in? Can you push something on there that the contacts will?
Reset.
If
Usually.
it's underneath from the bottom now, that other one would.
Yeah, sometimes they're on the side.
Okay, so can you see that there? No?
Yeah, this one here.
Okay,
is
show
on the
us.
side.
That would be what? That would be closing the
Right now,
contacts?
right now, this one here, and this is exactly what Steve's talking about, is to where this one here sucks it up to where now it actually reads on, and that's off. So if you put this in the upside down position like this, now it's being forced open all the time, and to close it, it's got to push it away, which it's not going to close. And
Steve, do you
so-
have something you show us a cutout that you
Yeah,
can
if
show?
we could get a real good zoom on this. Get my finger in the right place here so I can show you. This raises up when it's energized, and it depends on gravity when you de-energize it to drop back down. If you can see that cutout
So
of
there's
that.
no spring there, it's just using gravity to drop it out.
Right, this is just using gravity.
It's the same way with
So
this
if you
one.
turn it, okay, and flip it
So
around the
if
other
I
way, what
mounted
happens?
if I mounted it upside down somewhere,
It's already closed.
Exactly.
yeah, and it's probably not going to be as solidly closed as it should be, so it's actually going to be arcing, and you're going to really burn it up.
Got it. Okay.
And then you started to bring up another comment, Mike, about difference between contactors, starters, relays.
Yeah.
Of course, the difference between a contactor and a starter is this overload block here. If it didn't have this overload block, it's just a contactor. And the difference between a relay and a contactor has to do with the amperage, and that might vary with manufacturer, but usually about 30 amps, it becomes a contactor instead of a relay.
Okay.
Also, with multiple poles, your relay, you can have several poles, like 3 or 4 poles, but if you have something where you're switching like 12 poles, then it's going to be a contactor, not a relay.
All right. The principle's the
It's a
same.
manufacturer.
The principle's the same.
Yeah, principle's the same, it's just a sizing situation.
Power sources for the coil and the control circuit. There are 3 basic ways to provide power to a control circuit. All right, let's take a look at this. One, all right, here's the control circuit. You see the smaller lines, which is exactly what we're looking for. Now we're starting to get into control circuits. Here's our symbols. Normally open contacts, overloads shown normally closed. This, we haven't talked about that, but that's going to be an overload device. That's your motor. Here's your T1, T2, T3, your terminals to your motors. Line 1, 2, 3 coming in. Okay, so if I close these 3 main contacts, this motor will run. I got it. I come off of terminal 2 with the terminal. I go over through overloads in series with the overloads, and I bring power over from terminal 2 over to the motor. Now, in reality, voltage is actually traveling, to the coil. Voltage actually is traveling through the coil over to this one point right here. So really this is one phase voltage, and this, right? So right between this point and this point right here, I should measure how many volts. If this, 240, right?
240.
So that's another way for troubleshooting. So I have 120 coming in here. I have 120 going through the overloads, which are closed to this coil, continuing on, but I'm not shading that. We don't need that to that point right there. So in reality, that would be 240 at one point. All right. Let's see what else we got here. Okay, we got the 240 on the line. Oh, the question was, how do you get power? Well, we're just tapping right off of the line of the branch circuit conductor supplying that particular starter. Because Steve, you mentioned already, so I'm about to talk about it. Since there was overloads in that contactor, then we call this a starter. I don't know if that's an industry standard or if that's just something.
Yeah.
Dennis, what you got there?
Well, and I was just going to mention that a lot of times you're going to see that your manufacturer is going to have a lot of the material that you're covering or the wires that you're talking about there already pre-wired. And so you're coming off of your contactor, you're coming down, and you actually go down to your overload contact down here.
All right, let me show you what I got here on the screen, and then you show me physically where it goes. You ready for this? And we do one step at a time. This is T2, right here. Show me where that T2 is on your...
Right here.
Isn't it? Is it right there? Is it? Can you see the wire connecting to it?
Not on this one. This one just comes off of the coil itself right here.
I gotcha.
It has a screw on top where you could replace
Yeah.
put a wire.
Okay, so it would come off of right there, right?
Yeah.
Yes.
And then it goes over to the coil,
Here.
right there. And that's your terminal. And then the other wire that goes over to the start button or goes over to terminal 3.
Terminal 3.
Is it marked terminal 3, by the way?
Well, this one here is
Right there.
right here is 3. So
I see
here's
what you're
your
saying. I see. It's only having the... Okay, I got you, what you have there.
right.
All right, so the point is I'm trying to make here is how do you get power for this control circuit? We're coming off of the branch circuit supplying that actual motor. And there's a lot of rules associated with that, but right now that's how we get a source. Another way to do it is to go ahead and come off of the branch circuit conductor supplying that motor. Let's follow. Here's a disconnect. Okay, it's just a knife switch, isn't it? It's not fusible. So we close it, power comes over, so the M contacts are open, but if they were closed, then power goes through the overloads, to the terminals, to the motor. Okay, that's fine. That's irrelevant. How do I get the control circuit power? Well, come off of line 1, come off of line 2, and supply a transformer on the primary, which would then give me secondary voltage. In this case here, go from 480 down to 120. And we mentioned one of the advantages of control wiring is that you can operate with lower voltages. And here'd be an example. Do we have any of these? We have one that has a transformer in it, but we'll show that later on. We're not going to show it now. So that's another way. Tap off the branch circuit and then step the voltage down. That's number 2. Number 3, well, you know what? Just go to a breaker somewhere. This case here, pick up 120 volts. And the branch circuit wiring going to the motor is unrelated to the branch circuit that's used for the control conductor. That's the third way you can get power. Let's talk about the coil application. All right. We have a coil. Again, we keep saying motor control, and really it should be control and signaling. Let's see what we got here. We got line 1. We're going to this push button, I don't know if you can see it or not, but this push button is normally open, momentary close. Here it is right here. Normally open, push button, momentary close. So we go open. Let's follow here. Line 1 to the open button, to the solenoid, to the neutral. Right now, the solenoid is not energized. If I push button, this normally open push button, if I push it, then I will energize the solenoid. So if I press this button, I close the contact, I energize the solenoid, and if I energize the solenoid, it's going to draw in this armature, and this lock, a dentist office, you go to a bank, and so they press a button, it energizes the coil, it draws in the armature, and unlocks the door. Now that's called failed secure remote solenoid. And what that means is that pushing the normally open push button energizes the solenoid door lock. By pulling the plunger in, the door can be opened. Releasing the push button de-energizes the solenoid, allowing the plunger bolt to return to the lock position. And what it means by failed secure is that if you lose power, then that door is locked and you're not coming in at all. So you can see where a prison would probably be a good idea to make sure that if we lose power, then all the locks are locked. But then again, we might have next. Now this is going to be fail safe. The other one was what? Fail secure. So in a fail safe condition, let's see, we have line 1. This is normally, let's go here. Line 1, normally closed, solenoid. That means the solenoid is always energized as long as the push button is not touched because it's normally closed. That means that here is the door lock, and if it's pushed, then it will be locked as long as the push button is not pressed. So this one, if you press the button, then it will de-energize the coil, and it will then have this armature go the other direction because the lock is on this side here. Then it would unlock the door. So if I go to a doctor's office or I'm in any kind of facility and the doors are locked, let's say a bank, the doors are all locked, the whole facility. So if somebody comes in or a pawn shop, I say, I think I'll let that guy in. You press a button, well, the solenoid was energized. If you press a button, you de-energize it. Now the armature draws back, unlocks the door. And then, of course, you release the button, it locks it again. But if you lose power, you want to make sure that people can get out of the building. So if you lose power, guess what happens? As we show here, it's fail safe. If you lose power, then the solenoid retracts and the doors are unlocked. Eric?
This is one reason, because of the complexity of this system, that what's very common nowadays is just simply to use magnets. And you'll see the magnets on top of the door frame, and the magnets will hold the door closed. And so it's an inherently fail-safe system.
So what you're saying is that you're using a magnetic field. It's a solenoid, but except it's going to be drawing it, it's holding it closed.
Actually, yeah, it's just a magnet, and the door frame is metal, ferrous. And so the magnet just holds the door closed.
Got it. Contactors. Contactors are relay type switches used to open and close power circuits. They can be manually or magnetically controlled. So here's a manual contactor, line 1, line 2, line 3, T1, T2, T3. This is basically a toggle switch, isn't it? You press the start button, you're closing the 3 main contacts. There's no magnetic coil. This is just simply a manual switch. And then you press the stop button, which then manually opens the 3 contacts, and then the motor or whatever the load is stops. Over here, we're coming off of line 1, line 2, line 3. Oh, here's your line 2 providing power over to one side of the coil. Is that right?
Mm-hmm.
And then here is line 1. I don't know what it's going to be doing back here, whether it's coming back through here, going to line 2, but it's irrelevant. What matters is that if we get voltage to both terminals of this coil, we will energize the coil. We will then close the main contacts. Line 1, 2, and 3 will then provide power to T1, 2, and 3. Well, let's take a look at this picture here. All right, here is a magnetic contactor, single phase. Line 1 has power to one side of the switch. It's normally open. Line 2 has power to one side of the coil, even though the voltage in reality continues on to this point here. We're only just showing that really the coil has some power to it. If I press the button, then line 1 power goes over to the other side of the coil, and line 2 is at that coil. That coil is energized, and if you energize the M coil, we probably should mark these contacts as M contacts. It would then close those M contacts related to that M coil, and then you have line 1 to T1, line 2 to T2. If we go to a 3-phase, line 1, line 2, line 3, these contacts are open. Going to T1, T2, T3, power goes to the normally open push button. The M coil is not energized, so therefore T1, 2, and 3 is not energized. Press the normally open push button and momentarily close it. Since line 1 is supplying one side of the coil, now that you press the normally open push button, it was line 2 to one side of the coil. Line 1 goes to the other side of the coil. The coil now is energized, and it closes those M contacts. And now T1, T2, and T3 is being supplied by line 1, line 2, and line 3. The load is operating. Let's talk about magnetic contactors. And I think you guys had something where, Dan, do you guys ever push these contacts in to find out what's going on and measure voltages? Or because if you push these little tabs in, you can actually push the armature. You can make and break the contacts. And we've seen, I think, a couple examples where we're able to move something. Tell me about, in real life, in practice, what goes on?
People can do that. You can push in even like on this contactor. You can manually push those in. It's probably best to have your arc flash suit on when you do that.
Yes.
And with the newer regulations and whatnot, that's becoming less and less of a day-to-day practice.
Eric, what do you got there? Same thing?
Here's one right here. You can't get it with your finger, but you can get something to push this in with.
All right, let's
this has a little.
let's just talk about safety here.
Don't do this at home.
You know, in the 70s, and I worked as an electrician in the early 70s is when I started, we didn't have OSHA. We didn't have safety. And I worked in high-rise buildings, and there were no guardrails. I mean, you just simply, you walked off the building if, you know, you didn't pay attention to what you're doing, and things fell down and hit you in the head. And you know, there's a big change happening in the last 40 years, and now we have to be very careful of an arc blast. And this is not the time to talk about it, but we're going to slowly start bringing in safety applications. And that is what Dan is saying, is that if you push that, and Eric showed, well, you can bypass it because you couldn't push it with your finger, so then you kind of get something like a screwdriver, and then you kind of point it in there, that there could be an arc blast. And we're going to talk about that probably at the end of this DVD, if we have time. If not, we're going to get it by the end of the next DVD. But somewhere in there, we're going to talk about practice. And the number one thing is everybody wants to be able to, and you want to be able to have your employees, you want to make sure yourself or whoever is working leave the way you came to work. And people want you to do things that, you know, we all have done things, if you've worked in a trade, that we can look back now and say, that really wasn't a very good idea. And some people weren't able to survive the things that we got lucky that we got away with. So do not push that in there while the circuit is energized. If you want to lock it out, turn it off, lock it out, de-energize it, tag it, and then say, hey, then it's troubleshooting to find out do you have continuity there, or maybe an ohm meter to find out what's the contact resistance, you know. But you don't want to do that because it can be done. Any other comments you guys want to make at all? All right. All right, but for a fact, that can be pushed, and it's something that we don't want to do. Contactor power contacts. Contactor power contacts. Where there's no power to the coil, the main power contacts are opened. When power is applied, the energized coil closes the main contacts, which then energize the terminals to the load. We've kind of talked about that already. Let's see what we got here. We got coming off of line 1 to a normally open switch, going over to this coil. Terminal 2 is already supplying the side of the coil. That's your normally open push button. Line 2 supplies one side of the coil. Line 1 supplies the push button. Line 1 supplies the push button. From the push button, we're going over the other side of the coil. If you press this button, then you provide voltage to the proper voltage to the solenoid coil. That coil then closes the contacts, which we've talked about earlier, makes line 1, 2, 3 supply T1, 2, 3. We're already kind of ahead of the game on that one there. All right, 2-wire remote control circuit. Here we go. All right, normally open switch. Coil is de-energized. Come off of line 2. Close the switch right here. Well, if you close this is not a momentary close. This is just closed. Then of course the coil remains energized, and then the coil then closes the main contacts. This is not a motor. This is just a coil that's closing the main contacts that we're not seeing on this particular graphic. It's closing these contacts right here, except it's replacing this with a switch rather than a momentary close. Steve?
And what you just said can't be said enough, Mike, that's not the motor, it's a coil. That's one of the most common areas I see beginning students get so confused about.
You know why they get confused? Because I remember when I first got into controls, I didn't know what was the motor, and I didn't know what was the coil, because they were, sometimes they'll show, and I'm not saying in books, I'm just saying, remember when we were taking tests, with the graphics that were shown, they used an M for a motor.
Yeah.
And then they used an M that was supposed to represent the coil that operated the M contacts. So what you got to be careful is, if you take a look at the circuit, and if you look at if you understood enough about controls and you look at the whole circuit, then you'd realize, okay, if you had this drawing right here shown, then it's obvious that that is not the motor when you see T1, T2, T3 going to a motor. You understand? That's your line, that's your terminals. This is obviously not the motor, but when you don't know, like you're saying, and you're just getting started with that, this can be incredibly intimidating. And you got to say, okay, sit back, look at the logic you have here. You can tell that's not the motor, that's the control circuit controlling the M coil that closes the main contacts that go from line 1 to T1, line 2 to T2, line 3 to T3, and that's how it works. So you got to get a little bit more experience. But somebody who has a lot of experience wouldn't have been confused. So they don't say, why are you confused? It's come on, look at the circuit. But we don't have the knowledge sometimes. Let's go to remote control introduction. The 2-wire control circuit can be utilized in different ways by replacing the push button with a maintain contact switch. Well, that's one we just saw. So if you close the switch, right now the switch is open, it's off, coil is de-energized, turn the switch on, close the contacts, you're maintaining that coil, which closes the 3 main contacts, in this case here, so that we can then get power to T1, 2, and 3. A separate control circuit can be used to provide a lower voltage for the control circuit. Let's take a look at this. This is a 480 volt 3-phase contactor. We have 40 volts coming in, and actually I'll have Mike change these colors. We have black, red, blue, and we just use it in our office as a standard color code. Black, red, blue, white for 12208, and we use brown, orange, yellow, and gray for 277 480. It's really not related to the point here, but let me talk to you guys. What is the practice in the industry for you guys, Steve? What have you seen?
That's what our area where
Brown, orange, yellow for the higher voltage, black, red,
commonly,
blue?
you might get into some industrial locations where they might use all black and number them or something, but general commercial wiring, it's going to be brown, orange, yellow.
Eric?
Well, for us, 480 is low voltage, so it's black, red, blue.
Is that really true?
Yes, it is.
Well, I mean, I know it's true, low voltage is low voltage. I mean, 480 is low voltage
480
for Dow
is low
Chemical.
voltage, and so, yeah, it's black, red, blue.
Okay, well, okay.
You don't use
Dan?
bell wire.
Our industry standard is the same. We normally use the brown, orange, yellow. We have a lot of older equipment that doesn't have that.
What do they just use, all black?
Well, in the old days, it was a lot more common to use like all blacks, like 3 blacks, 3 reds. And if you broke a conduit, it was a lot easier to fix because then you hooked all the blacks together, hook all the reds together, hook all the blues together. Then all you had to do is check rotation. If you use all brown, orange, yellow, you have to get out the ohm meter and ring out each wire.
Yeah,
make
and,
sure
and if
which
you have
motor it
brown,
goes
orange,
to.
yellow, and then you had the wrong phase rotation, then you'd have the wrong color on the wrong phase
Well,
in
you
order to
might
get that
have-
motor to run.
Brown from one motor and orange from the next motor and yellow from the next motor.
Okay.
So
Dennis?
that's the advantage of using all the same color, even though you're not supposed to do that anymore.
Well, you can. There's nothing that says you can't, right? Use all the same color.
Yeah, you can. You just have to mark it at every junction box.
That's true, yes.
Yeah, and it's become industrial standard that when you're dealing with 120, 208, you look at, black, red, blue. When you go up to 480, typically it's going to be brown,
All
orange,
right.
yellow.
All right, so let's go on. So we'll go ahead and get this brown, orange, yellow colored on all our 480 volt graphics that we're working from. All right, so, but you know what? If we want, a separate control wiring so I can go ahead and run 120 volts though, and put a single pole switch. Let's say if that's what I was going to do, a single pole, single throw switch, and just provide power. So here's the neutral. Here's my coil terminals. All I got to do is get 120 volts to this coil and energize the coil, close 3 main contacts, and motor's running. So you could use 120 volt for controls, which is lower voltage. Steve?
Again, something that beginning people may be wondering is, how can we use just any voltage we want to it? We have to change the coil.
Oh,
To match the voltage.
Talk to me about that.
Well, maybe you buy that starter, it has a 480 volt coil in it, that's what you're going to work with unless you've got a different control circuit. Then you can take those screws off the front of that diagram we're looking at and take out the coil and put in a coil that's rated at the voltage that you want to use. So you have to change that out. You have to buy another coil at the supply house if you're not going to use what the starter came
Is that pretty
with.
standard?
Yeah, and you can order them in with any voltage in it that you want.
So if you
you're
knew what
ordering
you
them.
want in advance,
Yeah.
just
But
get
if
the
you
one
don't
with
know what you
120 volt.
Yeah, but if you don't know what you want in advance, you're just going to end up whatever they have on the shelf. So
Gotcha.
Yeah,
Makes sense.
one other thing before, if you look at figure A versus figure B, notice in figure A you're not using the overloads, the overload contact, where in and it tells you that in figure B. So I mean that's what's nice about being able to start to understand the symbols and looking at the figures.
Yeah, and so what we have here, and let's see if we've been looking at this, we've been dealing with contactors,
yes.
not motor starters. These are just contactors. This
Right.
is, and we're going to talk about why and the differences. We've talked about relays, we talked about contactors, starters, but really haven't put the whole package together. A couple times we've talked about it, but we'll do it again though. Let's talk about a lighting contactor. A contactor used to control lighting circuits or a lighting panel is called a lighting contactor. All right, let's follow this logic here. I got 6 circuits, line 1, 2, whatever. Let's say 6 circuits. And then I got 6 circuits leaving. So 6 circuits coming in. These, the neutrals are not being shown. And then I got a control relay that if I energize this coil, I will then close all 6 contacts. So if I want to turn on 6 circuits at one time or turn off 6 circuits, a bank where you got a sign and you got parking lot lighting and you want to be able to, it's not, a time clock is good for, 2 circuits. You get past 2 circuits, well then you can't use the time clock unless you use multiple time clocks. So then get yourself a lighting contactor, get a coil. Let's say here is, we probably should make this 120 volts. We'll make this a black and a white coming in on the line. And then we'll go ahead and run a neutral on the load side, and we'll make this a 120 volt coil. And so if I close the contacts of the time clock, I then would take 120 volts over to the coil. I energize the coil, close the 6 main contacts to the lighting contactor, then the 6 circuits will be energized. And what I like about this one here is a 2-wire circuit, is that in series, if I put a photocell in series with a time clock, so here is power coming in, let's say this is line 1 coming in, probably the neutral will be just running right through, and then, or I guess 220 is fine, line 1 comes in, and then if the time clock is closed, and if the photocell is closed, then the coil is energized, then the 6 contacts will close, resulting in the circuits being energized. So we have the time clock and the photocell in series with each other. And what I like about this configuration is that, because the way the sun, relative to the rotation of the earth or the earth on its axis, some time of the day, the sun, maybe sunset is going to be 5:30. And then during, let's say, the summertime and the summer solstice or whatever close to that period of time, it might not be until 8:30 sunset. Well, if you use a time clock, then you got to keep adjusting the time clock as the sun sets. But if you put a time clock, say, you know what, have the light come on at 5 o'clock. That's it. Well, it doesn't get dark until 5:30, or it doesn't get dark till 8:30. Well, then put a photocell in series with the time clock, because I don't want the lights to be on all night long. I like the lights to come on at dusk, but because this is a sign, and this is parking lot lighting, or whatever the case may be, I want to make sure that we turn off all the lights at 11 o'clock. By that time, guess what? There's not enough traffic. We don't worry about people seeing the bank. So you put the time clock supplying the photocell, and if the time clock goes on at 5 and cuts off at 11, but the photocell says, okay, today is 6:42 before it becomes sunset, well, time clock is closed, and the photocell has closed. Now the light energizes the contactor, the circuits become energized. However, at 11 o'clock, even though the photocell showed a contact being closed, at 11 o'clock, time clock says, we're opening, lights turn off. So it's a really convenient little way of doing it. We're now moving to Unit 6, magnetic motor starters. We just kind of got done with the contactors. This unit covers the operation of single-phase as well as three-phase magnetic motor starters. A magnetic motor starter is essentially a magnetic contactor with an overload relay assembly added. And Steve, you talked about that and you showed it earlier. And I'll have you get that device again. There we go. We show auxiliary contact. Here, this is the overload relays right there. So current comes in, goes to the make and break contacts, then it goes through the overloads. And we'll talk more about that. And then looking at Steve,
There's the overload block down here.
the overload block is right down at the bottom down there. Can you see the overloads from that one?
Yeah, right here in the front, this part that,
Oh.
if I, forward? That help?
Okay, yeah, I thought
This
there was a
very
better.
front
We
part
had some
that's-
overload somewhere else. I thought we had something, maybe Dan has an overload. Show us what it might. Okay, is there anyone better than that?
Actually, that's the heater mechanism of the overload, and then your actual, I don't know if you can see
Snap,
down
don't
in
want to go
here.
there. Just want to see the overloads, what they physically look like. All right, looks like Dennis has an overload in his hand. There's a couple different configurations, and so little devices that current's going to travel through. We'll get some better slides, and we'll show this in a second. So anyways, the fact is this. You got a contactor, and in addition to the contactor in series, before you get to T1, 2, and 3, if it's three-phase, we put a device in series that's going to be sensing current and heat. Now, one of the things that took me a while to understand, I'm afraid I'm going to get ahead of the game, but I have no choice. I'm afraid I'll forget it, is that when the overloads open, the overloads are not opening. Here's the overloads. They're heating up. What is opening is the contacts for the okay, let's take a look at it. Line 2, the overloads are in series with the coil, but these are the heaters. I know this is kind of like getting kind of confusing, and I'm not doing a good job. So, like I said, I'm ahead of the game, but I don't know how to do it. So let me just say that the heaters are the sensing elements. They are not going to actually open, but there's a set of contacts with each of the heaters that we're going to put in series with each other, that's in series with the coil, that if any one opens, then we drop out the coil. Do you have something, Dan, there at all that could maybe help the guys to see?
Where he showed that they put those in, these have different size wire
Yeah?
for different size motors. The finer wire would be for the smaller motors, and they're designed so that at the correct amount of current that goes through these, it will heat up to a certain level. Of course, then we're going to talk about, you have the bimetal switches that work, or you have the solder pots.
But 1 second, if we're heating up something, then if it goes past a certain point, it will then open a contact,
Yes,
right? The
exactly.
heater itself that you just showed me, current is still can go through it. Whether the contact open or not, the current can go through it.
Yes,
So the heater is just simply like the ability to capture the heat, transfer it to something, that something else measures the heat and says, hey, we have a problem, and it opens a contact. And it's we'll get there. It's just kind of like, I'm not quite sure. That's okay. I can understand that. I'll just go a little further, and then we'll keep building on this. Overload relay motor running protection. Overload protection devices are intended to protect the motors, the control, the branch circuit conductors against overloads that cause excessive heat. Now, there's different definitions in Article 100 that we got to be aware of. There's a definition of overcurrent. Overcurrent includes the condition of overload, short circuit, and ground fault. Now, what is overload? Overload is when you carry more current than something is rated. An example, if you had a 15 amp circuit breaker and you had 15 amp conductors and you happen to have a 20 amp load on a 15 amp circuit, well, the 20 amp load would be an overload condition because it exceeds the load rating of that circuit. Short circuits. Well, what's a short circuit? Well, if you go phase to phase, there's no definition of a short circuit, but you just got to know what it is. That's a short circuit. Phase to neutral would be a short circuit. Then you have a ground fault. A ground fault would be phase to the equipment grounding conductor, which would then have the fault current returning back via the source. So we're not looking to provide at this moment through the starter. Let me go back to the starter. This starter, we're not looking to provide any kind of overcurrent protection. We're only looking to provide overload protection. That's why they're called overloads. Overload protections are intended to protect the motors, the control, the branch circuits against overloads that cause excessive heating. What's an overload? An overload is when you have current exceeding the rating of it, but it's not a short circuit and it's not a ground fault. All right, let's understand what's going on here. When a motor starts, depending upon the code letter of the motor, depending upon the application, the easiest one to work from is the motor will start at 6 times its rated current, and it will start at what is called lock rotor current. We're not going to get into details to explain. This is covered in the theory course. So it starts at 6 times. It's standard number. It might be more, it might be less. It could be a lot more, it could be a lot less. It starts at 6 times for the starting current, then it goes to 300, then 150%, and eventually it runs. So let's just assume that this was a 10 amp motor. If this was a 10 amp motor, running current would be 10 amps, but what would be the starting current? 60 amperes. So we have a unique situation when it comes to motors, because let's take the lighting circuit. If you had 100 amps of lighting, well, when the lights run, you have 100 amps of lighting. When the lights start, forgetting about instantaneous, you have 100 amps of starting. Well, in that case, you could put a 100 amp breaker, let's say if it wasn't continuous, protecting a 100 amp wire, supplying a 100 amp load, because it starts at 100%, let's say, and it runs at 100%. But when you get to motors, if the motor starts at 6 times the running current, well, then you'd have a problem if you put a 100 amp breaker on a 100 amp motor, because when the motor first starts at 6 times its running current and it runs, let's say, at 100 amps, you'd have a 600 amp starting current on a 100 amp, let's say, breaker. For a 100 amp motor, it's not going to start. So the problem with, in order to provide the proper protection for motors, you have to size the breaker, or let's say the fuse that protects the circuit for the branch circuit. That's going to have to be sized considering the starting characteristics of the motor. And those percentages could be a lot of different options. But let me just distill it real simple. 43052 in the National Electric Code talks about, C1, talks about that there's a table that we use. And for circuit breakers, just for general application, you would size the breaker at 250% of the rating of the motor current as listed in the code book table, 430, 240, 248, 249, and 250, depending upon the application. So you get the motor currents on the code, FLC, you go 250%. That's to allow that breaker or fuse, that breaker to be sized sufficiently large enough to allow 600 amps or 600% starting current. That is going to be protecting that motor, though, and the apparatuses and the circuit conductors in the event of a short circuit. short circuits are going to be many, many more times rating than the rating of the actual motor running. So 250% protection for the motor circuit should protect the motor against shorts and ground faults. So let's go just a little further. Let's take a look at this example. Here is a 16 amp motor. We size the breaker at 250%, and if it's 250% of 16, I think that comes out to be 40 amps, or fuse, let's say. Well, this happens, fuse is between 150 and 300%. Circuit breakers are going to be 250%. I mean, depending upon whether it's a fuse or circuit breaker. Let's go with this here, circuit breaker. If we had a circuit breaker on a 16 amp motor load, that would be a 40 amp circuit breaker. And that 40 amp breaker is intended to protect this motor only against short circuits and ground faults. Here's a short circuit, draws 1200 amperes. That breaker is intended to open the circuit, short circuits and ground faults. Over here is the overloads. We call them the heaters. Again here, overloads and heaters. The problem is that the overloads and heaters are very slow responding. If you have a short circuit of 1200 amperes, these overloads and heaters are not intended to open under short circuit ground fault conditions. That's the purpose of the circuit protection device. However, if you put 24 amps of a motor that's supposed to draw 16 amps, and you happen to have a 40 amp breaker, well then that breaker is not going to sense the overload. So what we have to do for motors, we have to have overload protection, which is the overloads of the heaters. Then we need to have short circuit and ground fault protection. Now, we're not into motor circuits, and I'm almost sorry that I even got into this discussion. But I need you to understand those heaters are going to be sized a specific manner in the industry as well as a code. And they're there to provide overload protection, not short circuit protection. And I know this is code, and if you don't know code, we'll see if we can put a few sections in the back of this book talking about some basic NEC requirements, and that might be something that you can review. How do you size the wire to a motor, single branch circuit? How do you size the protection to a motor? Maybe some requirements, NEC requirements having to do with motor control circuits, maybe motor controllers. So we'll see if we can put something in the back of the book, a little annex in there about NEC requirements based upon the 2008. Time goes by, it's going to change. Let's go back. Overload motor protection is to protect the motors, apparatuses, and branch circuit conductors against overloads. Okay? Overcurrent protects against overload, short circuit, and ground fault. We are not protecting against overcurrent for motors, for heaters. We're protecting against overload. What's an overload? Current in excess of the rating of that particular application. Motors, what happens with motors? They start at 6 times the lock rotor current, the running current, and then they go to 100%. Because of the starting characteristic being different than running characteristics, overloads will protect the motor under running conditions. Short circuit and ground fault protection device protected under starting conditions or short circuits and ground faults. If you have an overload of motor draws 16, you draw 24, your short circuit protection devices will not sense it, but the overloads will. If you have a short circuit, the overloads are not intended to protect against short circuit and ground faults. That's the purpose of the short circuit ground fault protection device. The combination of the branch circuit, short circuit ground fault, and the overloads will protect that motor against overcurrent. But they're different components and they are sized differently. Now, the National Electrical Code says how you can size the overload protection devices. Then they get into temperature rise and service factor, and you got to go to the motor nameplate, and there's code rules that tell you how to handle all that. But we're going to put that all aside because in reality, you're going to be sizing the overloads by simply looking at the motor nameplate. Let's take a look at this graphic here. We're not going to get involved in the service factor and the temperature rise and all the other stuff. We're going to look at the motor nameplate, find out this motor has a nameplate current rating of 28 amps. Based upon the motor nameplate rating, we simply go to a table that's given by the manufacturers that's provided for that given starter. And Dan, you had that little tiny device. Any of those have a number on them? Any kind of B number, anything? Have something identified in some way? What does that one say?
The GE ones are actually pretty good because the part number is actually the amperage. C955A means that this one's good for 9.55 amps.
Oh, that's the GE.
Yes.
So, okay, and Dennis, what do you have?
This is square D, B19.5.
B19.5. Now, I don't know what that means. We'd have to go into a table like this right
Well,
here.
It's rated 19.5 amps.
Oh, is that right?
Yeah.
I did not realize that the numbers on the overloads.
A lot of them are, some of them aren't. This one, for instance, is an Allen Bradley, another American company. W77. This one is off probably a 125 horse motor. So you can see the amount of metal that we're heating up is quite a bit more in this one. So
Help me here, because I'm looking at this table that we have here on the graphic. It says 1 TU, 2 TU, 3 TU. What is that? Why are they different? Anybody have an idea what that means on that table?
Well, for the Allen Bradley bulletin that's like this, that would refer to the size of the starter. I'm not sure if that's what it is in this particular instance, but the first column would be for a size 1 starter. At this nameplate, you use this thermal unit number. For
Okay.
a size 2 starter.
Okay, I need practical here. And Dan, you're the one that's actually right now working in the practical application. How do you size the overload protection device that you put on? Are you using electronic and you're not even using these at all?
no, we use these. These are some of the ones from our mill. We start out at 100% of full load current.
All right, hold on. So I got a motor and it draws 10 amps. Then you go and you find an overload device that's rated how many amps?
10 amps.
10 amps. And you put that baby in there.
And then if it holds, we're all good. And that's because we're more on the maintenance side of it. We can go up to the maximums that are in the code, but we like to start out at 100%. That way you're protecting the motor even better.
Okay, so if we go back to the slide here, the code tells us, listen, you could set the protection device at 125% of the nameplate. If you
Yes.
want to. So in your case, if you had or in our example, if it was a 10 amp motor, and if it had a service factor 1.15 and up, and we go to this label and it says 1.16, well, it's 1.15 and up. Well, 1.15 and up and 1.16 is in that condition. Well, then I would set it at 125%. Well, I could set it at 125. But you're saying,
Yes.
you know what? We'd like to protect this motor. So we'll set it at 100%. And if it doesn't work, then we'll adjust it up. But we probably won't exceed the 125 because now you're allowing possible excessive heat. And you might not burn the motor out initially with excessive heat, but just a small percentage rise in heat reduces the life cycle of that motor substantially. So what do you do if what do you just go to next size up if it
Normally we'll take amp readings and see what it really is running at. And if we need to go upsize them, then we'll size them up.
is it possible the motor is just overloaded when you take the amp reading? In other words, it was supposed to draw 10 amps and it's drawing 12?
Well, yeah, if it's a,
In other words, the motor might not have been properly sized for the application.
that's correct.
And so that's another way, by taking the amp reading and finding, hey, listen, we have a bigger problem than just overloads here. We got a motor that's being stressed, that's being used an excessive amount of current, that's going to be overheating and ultimately going to be failing.
Then we'd want to look at upsizing the size of the motor to be correct.
Dan, Dennis, any feedback? Anything
No,
else?
I agree.
All right, so we get the nameplate rating. We size it 100%. Maybe this is, and then of course you can kind of go to the table. The manufacturer will have the tables inside the contactor telling you what size and maybe what kind of thermal number that would actually be used for that given application.
Mike, I think what they're showing there on the top, the 1 TU, 2 TU, and 3 TU is the number of thermal units. So that left column would be a 120 volt application, and the second one is a 2-pole starter, a 240 or a 208, just using 2 lines, and the third one is your 3-phase.
Okay. And so you'd still use this B039 for these combinations. So that's allowing to go, 1, 2, and 3 pole. All right. Overloads include, well, when would you have a case of excessive amount of current? Well, there's low voltage to the motor. Anytime you reduce voltage to an inductive reactive motor load like that, you're going to create increased current. Eric?
If you've got a motor that's hooked up to a fan and the pitch of the fan is too high, you'll overload your motor.
Then it's being stressed.
Right.
Lock rotor current. I mean, the motor locks, something jammed. Someone was supposed to go through, and all of a sudden it jammed. And now the motor is struggling to turn, and it's locked rotor, and it's drawn back at the 6 times. Motor's just too small. Unless your fan, I mean, it's too small, or whatever the case may be. Bad bearings. I think I heard somebody talking about, I don't know why I just hear this recently, about bearings to some large motor that the bearings just kind of wiped out. Well, if the bearings go down, obviously it creates a lot more drag and friction, and motor starts carrying excessive amount of current. Single phasing, where you have a 3-phase motor and then one phase drops out. I can't remember, what is it, 59% rise in current on one phase, or whenever you single phase a motor, I forgot exactly what happens to the current and percentage of the current. But either way, if you have a 3-phase motor and you single phase the motor, meaning you drop out one phase while the motor is running, that motor could continue to run, but an excessive amount of current, that's overload. It's not short circuit and ground fault. So we want to make sure that we provide protection against that. Let's talk about different types of ways of providing overload protection, and remind me, I think I remember this. All right, what can we use for the overload device? How do you say this, Eric? What's this?
Eutectic.
Eutectic alloy. What's eutectic mean?
It's a metallurgical word that means that a combination, an alloy of metals melts at it is like a minimum point temperature.
So it's like they can tell what that's going to melt at.
Yeah, the eutectic alloy is a mixture of metals that the percentages of the mixture is such that that percentage causes it to melt at the lowest point of that percentage of those mixtures. Solder, in other words.
I haven't been able to yet describe this, but here is a symbol for the overload. When current travels through this device here, it creates heat. This heat has this ratchet wheel already turned, and here's a ratchet wheel right here, and this pawl is going to a set of contacts. And the way it's set right now, the way this ratchet is turned, and maybe Dennis, you might have one there. Let's see if we can zoom in on yours right there. There's a pawl right there. And if you try to turn it, Dennis, you can't turn it. Is that right?
Solid.
It's solid.
Very solid.
But if it got hot enough and it's eutectic alloyed, it would melt, and then all of a sudden it would release.
And because internally in your contactor in here, this is a spring-loaded mechanism. So, I mean, if we could actually physically look in here, you could see a ratchet or an arm that holds back on this wheel.
Now, behind each of those, well, those heaters are going to go, there is a set of contacts, little contacts. And so we have the heaters that are heating that eutectic metal, and when you press that reset button, you're loading up the ratchet, and you're loading up the contacts, and you're closing all 3 of those contacts internally.
Well, typically there's usually only one contact, which is off to this side right here.
Okay, there's one that would,
Right.
okay, the ratchet, okay, any one of the 3, though, would heat up, would release that contact that's being held closed.
Correct.
So you press the reset button, it loads it up, it closes the one contact for the overload, and any one of those 3, if they melt because of heat, would open that contact. And let me go ahead and find that picture right there. Any one of these 3 could melt that eutectic metal, releasing the latch, causing this contact that was being held closed to open. Are we there, guys? Is that okay? Am I saying it right?
Exactly.
Okay. So now let's go take a look at it right here. So when you press that reset button, it pushes this down. Right here. Here's my control circuit right here. This is the control circuit. It pushes this down, so now my overload is closed and is being held closed. But here is the line conductors. Line coming in, line 1, and let's say T1 going out. Current travels through here, travels through the heater. It heats this up, travels to the load, and if it heats it up to a certain temperature, it then will melt the eutectic alloy inside here, releasing this ratchet, as shown right here. It just turns it, and all of a sudden, the control circuit contacts open. The heater is only allowing that contact to open, but the heater still would have continuity even though the control circuit contacts open. Let's take a look at this one here. So, we press a button, we load it, we close the control circuit, the contacts, the overloads are closed. There's an overload condition, it melts the alloy, it then releases because there's a spring action there, it releases it, now opens the overloads, and of course the overloads being used in a circuit would then stop the circuit if that was the purpose of that. What do? Well, you have to make sure the alloy cools sufficiently. Once it cools sufficiently, then you can press the reset button and then reset the overloads. So it really is two parts. You have the contacts that are normally open that'll be set closed, and it's the heater that would be releasing the energy that's holding that closed. It's important to remember that there are two parts of the overload. I just described that. The actual overload device and the closed overload relay contacts. Here's the overload device, and behind that is the contact, and that allows us to reset that contact. Any comments? Extreme care should be taken if the contactor has been de-energized because of an overload.
There, Mike, it's because something happened to that motor to call for more ampacity to keep the motor running. Either the bearings went bad, it got hit by a forklift, something's wrong with that motor, and I've actually seen demonstrations where contactors explode because they get reset without somebody going out and physically looking at the motor.
So anytime the motor drops out, the starter comes out, there's a problem. I mean, it's like a GFCI. If a GFCI trips, there had to be a reason that the GFCI tripped.
Right.
If the circuit breaker tripped or the fuse blew, it isn't like, well, let me just press the reset button and we're fine. Or let me just go ahead and close and disconnect again. Or let me go ahead and replace the fuses. We got to find out, well, and what you said, Dan, was, we put an ammeter on there. What happened?
Okay.
I mean, something had to happen. Why is this thing drawn? Why did this thing burn out? So you don't want to be going in there and resetting that without knowing what was the condition. Overload relay symbols and schematics. Now, I'm confused about this particular graphic right here because we show 3 overload relays, and then we show all of them together. So you guys got to help me because you're the experts. Is there one only, or is there 3 in series with each other that any one of the 3 could open in physical, practical sense?
Yes.
Depends on the manufacturer.
Okay.
And the older style ones did have 3, and they had 3 reset buttons.
Oh,
3
Steve,
there.
here, look at Steve's. Steve,
There's-
show us the
there-
3 reset
it's-
buttons.
Well, you can see that there's 3 heaters right here.
What are the 3 reset buttons on it?
Well, each one of them has their own set of overload. Well, no, there's not 3. This one must be on an automatic reset.
So, okay, what is the practice today? Is it a single overload?
Almost all the new ones have one overload switch that's by any 3. The older Allen Bradley did have, and in the 60s,
Yeah,
they only
like
had
this.
2, and then I forget
That's
what
right,
code
because the
change it
code-
was, then they had to have 3. And the
All right.
ones that had 2 did have individual switches.
All right, so really, whether it shows it one for each one, or whether it just shows all the overloads individually, basically it comes down to this. Whether it's 1 or 3, you come off of line 2, you're going through the overload contacts that are being held closed mechanically, that goes to one side of the coil, and if you provide power to the other side of the coil, then you energize the M coil, which closes the main contacts motor runs. If any one of the 3, or if there's just one, however it works out, opens, it de-energizes the coil, opens up the normally open M contacts that were being held closed. Here's another example how it's shown. I like ladder diagrams. I mean, looking at that right there, to me, is just a lot more work than, okay. A stop button's in series with the start button. We haven't gotten to auxiliary contacts yet. And then here's the overload. So if I press the start button, energize the M coil, as long as the overloads are all closed, well, then I can energize the M coil and it's going to do whatever the M coil does.
Other than the manual starter that we showed and talked about earlier, the overload is going to be the only thing that you put on the load or the line 2 side of the coil.
Okay. Other than a manual starter, on the line 2 side is going to be the overloads, but that's already built in the contactor,
Yes.
right? I mean, the line 2, do we have that as shown? The line 2 is connected, and the overloads are already rewired. So let me go back to this picture here. This line 2 connection through the overloads to this side of the coil, that's taken care of. Okay, you got that on your Dennis there?
Yeah. That's what we were talking about earlier.
Yeah, that's already pre-wired, so we don't have to worry about that side of the coil. So if the overload's open, that's all done internally of that starter. If it opens up, we just got to make sure that we get the control wiring. We're working on line 1 side is to get the controls, to get that coil energized or de-energized and whatever the application is going to be. I like that, good point. Troubleshooting an overload condition. In a new installation, repeated overload trips may indicate the next size up overload is necessary. And we already talked about this and the different things about troubleshooting and finding out what's the problem. Here's a little larger selection. It's in the textbook there of devices and the numbers and how it all works out. And you're going to get this from is that on the inside cover of the starter that has this number in there?
On the MCC door,
Yeah.
typically, yeah.
So you open it up and then the information is going to be right there. We're now in Unit 7, Basic Control Circuits. This will be the end of this particular DVD. We'll finish up Unit 7. The basis for most control wiring is either a 2-wire control circuit or a 3-wire control circuit. The 2-wire control circuits are used for self-starting applications such as pumping stations, air conditioning equipment, refrigeration equipment, etc. All right, let's take a look at a 2-wire control circuit. We discussed earlier that line 2 through the overloads to one side of the coil is automatically taken care of by the contactor manufacturer. Is that a statement that I can make that is a true statement, guys? Dan?
Yes. Yes.
Everybody? No, so that takes care of that. So we're not going to worry about, and we'll make sure that we won't color that side of the coil. We'll keep it black because we're not going to be messing with it. So now we're going to come off of line 1. If somehow I could get power from line 1 to the other side of the coil, I'll energize the M coil, and by energizing the M coil, it will then draw in and close all the M contacts. Now, they're not identified, but this is an auxiliary contact that will be held closed, that will be brought in closed. M1, 2, 3 contact will be closed. If I can somehow get voltage to the other side of the M coil, because we have voltage now to this side. So I go to line 1. I come over to some device. It could be a pressure switch, a mechanical switch, all the different types of pilot devices that you taught me, Dan. They're pilot devices. Whatever it takes that causes this to close, if I can then take line 1 over to a 2-wires circuit, which is just a toggle switch. I mean, just a switch. If I can close this contact, that then would get me power over to the M coil, and the result is that energizes, closes the main contacts, motor will run. All right? And by the way, as this is shown, and we probably should make this maybe black, is that this is already pre-wired. So all we have to do is come off of line 1 and then go over to this one terminal here, and the auxiliary contact would be, is it always marked as number 3 on the contactor?
Normally it's marked as number 3, yes.
Okay, so normally, so then we just come off of line 1, go to your 2-wire device, and then come off of that device and go right back over to this particular terminal. And my guys, take a look at the contacts now. All right, let's take a little bit more. A 2-wire control circuit shouldn't be used where automatic restarting after power loss will create a safety hazard for personnel working around the restarting equipment. Let's look back on this again. All right. If this was closed, because the water level or the flow or whatever the case may be, then this would be energized, the contacts would be closed, the motor would be running, and if we lost power, then the motor would stop. But the moment power came back on, since this was being closed already, this will automatically restart every single time you have power. Let me give you some examples where it'd probably be a good idea. You have an air handler. You got air conditioning. Well, if you lose power, well then, obviously, no power in the building. But when you have power come back on again, well then your blowers, your air handlers, your equipment will automatically come back on again. And that would be a practical application. I didn't work in a hospital, but I've done work in hospitals. When I was a contractor, I did a lot of energy management control where you would go into the control circuit and add another device in series with the control circuit, which you talked about, and by putting another device in series, and the rule was, okay, if the electric meter started measuring the current or the power and it realized that it was going to start getting into peak current, you had all these different devices in this hospital, what could we start load shedding by turning off? And all we had to do was put like a little, I think you have one of those little ice cube relays, put that in series with the control circuit and control it with a separate control circuit. So here I have a control circuit from a computer controlling the ice cube relay that made and break the contacts to the control circuit. So here's a control circuit controlling a control circuit. But we were able to do that with very small wire. Well, the problem is I went to this hospital. All the air handlers were not on a 2-wire control circuit, but were on a 3-wire control circuit, which we'll talk about in a second. Now, a 2-wire control circuit means that when you lose power, it goes down. When power comes back again, they automatically come back. On a 3-wire control circuit, when you lose power, everything goes off. But when power comes back on again, you'll see that the loads do not automatically come on, but you have to somehow take some other action to turn them on. So you can imagine how inconvenient it was for this industrial facility, this hospital, that every time they lost power, maintenance had to go around and press all these air handlers to turn them all back on again. So there's an in application. So 2-wire control circuits, it's great because you lose power. When it comes back on again, everything will work fine. The motor will run if that's what you want, but maybe that's a safety hazard. Can you give me some other examples where it would be a safety hazard for a 2-wire control circuit?
Well, maybe not a safety hazard, but if you're buying your power with peak demand, and if you have 100 motors that all come on at the same time, you can really mess up your peak demand and get penalized.
Good point. So you want to be able to stagger things in some way.
Well, going back to your safety hazard, if your overloads trip, you'll be standing right in front of that breaker when you reset them. So if it's 2-wire control and it's still turned on, you may want to make sure it's off before you reset your overloads.
Gotcha. Caution, the terminal numbers found on a schematic won't always match up with terminal numbers found on some wiring devices. Wiring must always be based on the function, not the terminal numbers. All right, we have number here. You might have seen throughout the textbook, we got a number 1 here, and then we got a number 1 there, and then we got a number 3 there, and then we got a number 3 there, and we have a number 2 there, and a number 3 there. In some cases, this is probably a number 2, and this is probably a number 3, but we got to be careful that there is no universal numbering that, okay, just take from this number, it's going to go to this number, because these 2-wire control devices have no numbers at all. So the numbers that we're using is just a way for us to communicate in the textbook, communicate in the video, that you can see, okay, that goes to there. That's no more than that. So we're just using these numbers for convenience. So you're going to have to know your devices, understand the application to make those proper connections. Optional wiring. Schematic often indicates optional wiring by using dashed lines with instructions. All right, let's see what we got here. We have this particular, will show us, okay, you can take, let's go here. All right, line 2 goes to the overloads. Okay, that side of the coil is taken care of. We're not going to worry about that. This wire here from the side of the coil going over to number 3, if that were number 3, that's automatically done by the manufacturer. So, I got a float switch right here, and right now I set it up so that it's a normally closed, so if water or the liquids rise, This is going to allow, the way it's set up, the way it's set up right now in this part of the circuit is that when liquids fill in, it'll stop. This allows water or liquids to enter. But it shows you the optional, well, if you want to, you don't have to connect it to the normally closed float switch portion. Connect the normally open, that would allow liquids, that as soon as liquids rise a certain level, it would, 1 second, is there a difference? This one allows it to come up and then stops it. Oh, okay. This one, all right, this one purposely keeps the motor contacts energized to have maybe liquids come in and then stop. This one is liquids might be coming in through some other source, and then it would close the contact. If you use the dotted line, you got rid of the top portion, then you'd energize the coil. Did I make it clear, or did I make it worse? Let's try this again down here. All right, line 1 comes over here. It's a normally closed contact. Guess what? This motor is running because it's normally closed. If this float rises for whatever reason, well, then that coil, rather, is energized and more or less running. The coil will be de-energized. If I go with the optional method, which means I get rid of this section here, then, since it's normally open, this coil is not energized, main contacts are not closed, motor is not running until the float switch is closed. So this gives us the option. It's kind of like normally open, normally closed that we talked about earlier. You know, which way do you want to use it? What do we got here? I guess we're repeating. Okay, this is close, energize. When a wire is used on the normally closed contacts, the circuit can be used to automatically fill a tank. So normally closed contact, the water rises, levers, stops it using the A wire. And we come off of line 1 over to the normally closed. Another showing it. Pump is running. F float switch contacts are closed when liquid level drops to a certain level. Float switch contacts open when liquid level rises, turning on that motor, turning off that motor. Kind of being somewhat repetitive, but that's okay. All right, what about if I don't go with A, but I remove A and I go with this portion? Well, now it's normally open. That means that the pump is off until the water comes up. Then it closes the contact. I think we have it right here. It's off. Coil is de-energized. If the water rises, it closes the contact. Now it energizes the motor, possibly to have that liquid be removed. 3-wire control circuits. And this is one of those, it's automatic. It goes up, it turns on, turns off, it turns off, it turns on. It lose power, some power comes back on again. It's just going to go back to its normal sequence. There's no requirement to get involved. And it's kind of convenient for most applications. 3-wire control circuit just changes a little bit. It's used where the automatic restart of equipment, it's used where, 3-wire circuits should always be used where the automatic restart of equipment after power loss presents a danger. We don't want the equipment to come on if we lose power to restart it. A basic 3-wire control circuit consists of 3 control wires, kind of obvious, 2 momentary contact push buttons, 1 to start it and 1 to stop it, 1 set of auxiliary holding contacts. Now, this is the first time we're going to start using the auxiliary holding contacts that we've talked about multiple times. All right, let's take a look here. Line 2, the yellow, is already pre-wired. That takes care of one side of the coil. It kind of goes right through the heaters, takes care of that one side. If we can get power to the other side of the coil, well, then the coil is energized. So we come off of line 1, right here, and we go over to a stop button, which is closed. Then we take that and go over to a start button. And the start button is normally open. And it also takes power over here to this normally open contact right there. And we're going to talk about what happens when you press start. You know, looking at the pictorial, it's hard I really like the ladder diagram. My
Exactly.
gosh. I thought I liked the pictorial, but you really can't understand because here's normally open over here, normally closed here, here's normally open here, but you don't realize that this normally open is in parallel with this normally open over here. You know, it's hard to see that where if we come over here, okay, I got my stop button, line 1 to stop, which is close. Then I go to the start button, which is in series with a stop, but it's open, momentary push button. And then there is the M contacts, and this is the auxiliary contacts, which are right there. There's your auxiliary contact, open. Here's your start push button, open. Here's your stop button, close. Stop button is a series with the start button. This is closed. This is open. This M contact is in parallel with the start button. And let's look at the wiring diagram here. Let's take a look at this one. All right, I come off of line 1. I go to stop. Well, this is not too bad. I go to start. And the start wire goes to one side of the auxiliary contact. And then on the load side of the start button, which is momentary open, momentary close here, I go over to 3. All right, I understand that. Eric?
The nice thing about the designation of terminals 1, 2, and 3 here is that the 1, 2, and 3 are the same for all different diagrams. So it's
Yeah.
easy to go back and forth and see which point is which on the different diagrams. So it's a real good teaching aid.
So by us using some numbers, we can all kind of get to point 1. As
Yeah.
you know, we can all go to point 2. What's the voltage point 1? All right, so now let's work some examples. Here we go. I got power now going to line 1, goes over to the stop. It goes over, supplies one side of the start, supplies one side of the auxiliary contact. Now let's take a look at this part right here. I'm going to stop right here. I want to go, it's right here and there. Or here is through the stop. And now I'm supplying this start and power is coming over here. Is that right? So this is energized to this point. So point 1 has power, point 2 has power, and this auxiliary contact, which is in parallel with the start button, I'll call it line, has power to it, or has voltage. Not power, voltage. All right? Then if I press the start button, well, now I have voltage going to the M coil. Let's go back and take a look at that. If I press the start button, I now have voltage to terminal 2. I will put voltage to terminal 3. Voltage will go over to this point right here, which is connected to the black wire, which gets me to the coil. When I press the start button, I am getting voltage to the coil. When you energize the coil, it will close all 3 main contacts to the motor. When I press the start button, I energize the voltage and get the voltage to the coil, energizes the coil, close 3 main contacts. These T1, 2, and 3 is energized, and this auxiliary contact, which is connected to the same coil, reactive, that contact that was open now will be closed, and the one that was closed in the auxiliary contact will be open. So I press the start button, energize the M coil closes the M contact. This is all, in this case here, just as I'm holding it. Then, when I release the start button, I have voltage traveling from 2 through the closed M that was normally open to now held closed M coil, energized in the coil. And that's called the holding circuit. Isn't that a latching circuit also? Or an interlocking
Holding
circuit?
contact.
You know,
Correct.
holding
Memory.
contact,
Right.
Memory circuit.
Memory.
memory circuit,
Or CLN.
Ceiling.
sealing it in, whatever the trade guys are going to call it. So let me go back to this again. All right, right now the coil is de-energized. M contacts are closed.
Open.
M contacts are open. Press the start button. Energize the M coil. Close all the M contacts. Main motor contacts are closed. Motor starts. This M contact that was open will close. Take your finger off and using the holding contact, the interlock, the latching, the auxiliary contact, that coil keeps that M contact closed, which allows now that motor to continue running after you release the momentary start button. If we lose power at this point, or if we press a stop button, either way, we de-energize the coil, and that opens that normally open M contact that was being held closed, resulting in all M contacts opening, coil de-energizes, motor starts. Back over here, if we were running and we lose power, then we're going to end up being in this state right here. The motor will not restart. You have to manually go in and press the start button. Now, I don't know. I live in a rural area and we lose power all the time. I don't have a factory there, but I know there's factories in our community. They lose power all the time. So I can see this could be a problem where you're worried about safety because you want to make sure that if you lose power, it turns off. But do you have like a lot of buttons that you got to go around push every time? Do you lose power a lot, Dan? I mean, is it?
We lose power from time to time, but the safety factor is that there's a lot of equipment that you wouldn't want to restart when you get power back. You would have to clear out conveyors or make sure that the next step is ready to accept what you're going to give it.
So if you lose power and you have this assembly process and conveyors and everything all tied in together, you don't want power to come back on again and everything is normal. You're saying, hey, when power comes back on again, we need to now take everything off the assemblies. We got to start this one process first, get that going, then get the next one going and get the process that we know is going to work the way we need it to work.
Yes,
Because
we need to restart everything in the proper sequence.
I like that, in the proper sequence,
Right.
not just start going around pressing all the start buttons throughout the facility. Eric, what about you guys? You Dow Chemical. I mean, you guys must have thousands of push buttons.
Yeah, we also have process computers, but that's really the least of our problems, or the least of the issues. You have a power failure, something comes down, that's a major issue. Because if you start a motor before the process is ready for it, you could overpressure something, a pressure relief valve could blow, and you could have a loss of primary containment. So you have to, as Dan said, start things in the proper sequence.
So I guess then in your case, you're concerned about power quality in the sense that you want to make sure you don't lose power. The number one thing is don't lose power, because the startup sequence, just losing power for a second could take you a long period of time to start the whole process to get to where you were when you lost power that instant. Am I right about that?
It could easily take a day to start something back up.
Just to get everything back to where
Right.
1 second down, we got a day trying to get it all up and all the. And I guess there's a lot of tension as to whether or not everything is being started in the right sequence and everything is going correctly until it gets going again. So I can see there's a lot of tension there. But safety. All right, let's go on. Wire diagram for a start-stop station. A ladder diagram and a start-stop push-button station labeled with numbers shows where the control conductors are connected. And that we talked about this. And arrow lines indicate connections made by the installer. Plain lines without arrows are also used. So these numbers are not universal. They might be common to some manufacturers. So you're going to try to be careful you control that you make the connections according to maybe the numbers on the manufacturers, or make sure you have to check your continuity tester, make sure that's a normally closed, that's normally open, and connect these devices. Is it a problem? Because I don't do controls, But if I went out there, started to go out and do controls, am I going to have a hard time? I would have liked to see numbers, and you're telling me the numbers aren't always the same. If I was hooking up a 2-wire control circuit, I don't have to know the numbers. Is that right? I just got to get off of line 1, and then I got to drop it off on the other side of the coil. So that's a pretty straightforward thing. If I'm doing 3-wire control circuits, just 3-wire control circuits, are the numbers pretty much on the auxiliary contacts and the contactor that a 3-wire control circuit, these numbers that we've been talking about are okay?
I wouldn't say so.
Okay.
You just wouldn't ever trust numbers. The numbers are great for this
I got you.
graphic right here, because you can see in the 3 different diagrams where each terminal is. But what you have a big problem also out in the field that, let's say that your equipment needs a momentary push button, and yet you have a maintained switch. And sometimes you think, well, wait a minute, I'm wiring up a maintained switch, but the equipment needs momentary, and you run into these kind of issues all the time.
I want to put this in practical terms because, yeah, I'm sure a guy can watch a DVD and he can read a book and he can answer the questions in the unit. But I'm more concerned about how hard is it somebody who doesn't have somebody he's working with to be able to do controls if you just watch the DVD and you read the book and you get these devices. Would you have to get a continuity tester to check these things? This is not... I mean, when you have experience and you got the same product, same manufacturer, you know, it's like you've done this enough times, you know, it's intuitive. But what about a person who hasn't done this enough time? Is this something that you really need to pay attention?
Yeah, it's something
think
you
so.
really need to pay attention, and most of them are marked normally open, normally closed, so you'll have that.
Okay.
Some of the discrepancies come in with the type of equipment you use, like we talked about NEMA starters. Most NEMA starters will have 2 and 3, will be pretty consistent. But IEC starters, like the one we have right here, we already talked about, its auxiliary contact is number 13 and 14. So different brands, different manufacturers may have different numbers. But the normally open, normally closed, you really have to pay attention to that part.
When I think, Mike, also, if you take and you actually do like what you said, take a meter and actually start, you know, physically connecting, you know, put your meter on continuity and just go through
You need
the
to do
contacts
that.
without being energized. Go through the contacts and close it, manually close it, reset it, you know, just figure out how this thing functions without having to tear it all apart. And it's going to make a lot more sense that you're going to find the normally open contacts, you're going to find the normally closed contacts, so it's
Okay.
going to click a
So
lot easier.
I really like what you're saying there. So if you haven't had experience, you're going to get your continuity tester. You're going to find, okay, goes here. Okay, oh, I see. That's line. Okay, that's the overloads. Okay, that's the auxiliary contact. That's closed. That's open. I understand how this works. I know that all I got to do is get voltage to one side of the coil. I'm going to tap off a line 1. I'm going to go somewhere and do something with it. And if I can somehow bring voltage to the other side of the coil, that coil is going to energize. Those main contacts are going to close. Now, what happens when it happens? I mean, what happens after that? Then we need to follow the logic. Okay, what do I want? Well, I want that when somebody opens this, that I want the motor to come on. Well, then that's a 2-wire control circuit. And when they do that, okay, that's just contacts. No, I want it because of safety. I want to make sure that if we lose power, you have to start the process. You know, so as you take, I think one of you guys said, it might have been Dan, that you layer. You do one thing. What do you want to get done? I want to be able to start this thing. Okay, then let's get that. I want to be able to stop it. Okay, well, then we need to add a series stop button. Normally, it's a normally closed, momentary open, or whatever the case, depending on the circuit. So I can see, personally, you gave me, Dennis, okay, yeah, I can physically get this. I can check this. I can check my devices. I can get a piece of paper and draw out what I'm trying to achieve. And you know what? If you can't draw it out to what you're trying to achieve, I guess what I'm picking up here, don't start screwing around with pulling any wires and making any terminals. Am I right about that?
Yes.
I mean, you need to get, okay, I got my contactor or my starter, and I need to be able to know exactly what's there. I got my devices. I need to know what I want to achieve. I need to be able to draw this out. Like I've said, to me, I believe somebody doesn't understand something if you can't explain it to somebody else. If you can't explain it to somebody else, then you don't understand it. And you should be able to explain it to somebody else who doesn't have your knowledge. And you should be able to break it down into simpler terms, basic elementary concepts, making some kind of relationship to something else. And if you can't do that, then you really don't understand it. So if I can't sit down and draw the circuit out on paper, then I need to get with you, Eric. Hey, here's what I'm trying to achieve, and here's what I think. Or get with you, Dan or Steve, right? And be able to draw this thing out and understand it and be able to see the continuity tester and say, okay, now, before I wire everything, I get my start button, I get my stop button, I get my contactor, put it together with a couple 18-gauge wires just right here on the table, right? Like on a lab, in a classroom. And then, okay, Take voltmeter, 2 guys. Okay, here, I'll press the button, I'm checking. Oh yeah, that would be there. Okay, I see how that's going to work out. That's what would give me the confidence. Then it's like, okay. So if I had a garage door opener, I'd want to do the same thing. I need to know it until I gain the confidence to how to work it. So hopefully this will help you learn to be able to draw it out, like we showed on, on a piece of paper, hand drawn. Understand your equipment, your contacts, the switches. What are you trying to achieve? How does it work? All right, and we learn numbers. It's great for the book. It makes it easy, but that's not the way it's going to be in the field. Well, let's move on to low voltage protection. Low voltage protection only applies to magnetic controls. Let's see, what is this right here? Built-in low voltage protection of a 3-wire circuit. All right. Apparently, the start button has been pressed, so we have voltage across the holding contacts or the auxiliary contacts. The coil is energized. M contacts are closed. This M contact's being closed. Everything is running fine. If I lose power, then I have 0 volts at the coil. Then the auxiliary contact opens, and so that's the end of it. Power comes back on again. Well, it comes back on again, but the process can't start, and that's where that low voltage protection, where the safety comes in. I'm not sure about low voltage protection. That's the right word. It might be an industry term.
It's an industry term.
To me, I'm thinking low voltage protection of the motor, not protecting somebody from it restarting. But if that's the industry term, that's what it is. So what do you do if you lose? Let's go back here. It runs. Everything is fine. Power disrupts. No power at all. We had no voltage there. Power comes back on again. Well, the problem is, you got voltage to one side of the coil, and you have voltage coming to your start button and your M contact, but we can't start that motor, we can't start the process until we energize that M coil again, and that only can come from press and restart. And that's called low voltage protection as an industry?
The reason, Mike, that it's called low voltage protection is because the coil, the M coil, will drop out at a certain percentage, say 70%, 60%, whatever. And so when the voltage gets to that point, the coil drops out and protects the motor from running at a voltage even lower than that.
All right. So we're talking 2 separate things here. We're not talking about safety, even though a 3-wire control circuit is when you lose power, it doesn't restart.
Right.
I mean, that's just, we talked about that earlier. This is like, no. If we come back over here in this original example, if this voltage dropped down to not 0 volts, be this same power disruption. If it goes off, you're not having any low voltage protection. But if this coil was operating at, let's say, 190, and that coil doesn't have enough voltage to operate, well, that means, guess what? Your motor doesn't have enough voltage to operate. Mm-hmm. That low voltage protection is that the lower the voltage, there's a threshold where the coil drops out.
Right.
That's going to protect the motor. And then when power comes back on again, well, it won't really matter because you have to restart it for safety applications, but you're still going to go back to the same procedure, that once you restart it and you go back to the whole sequence that takes us back there, if that voltage goes down, that coil's going to drop out, open up the circuit, and we're out of the game.
And then in the 2-wire control, they call it no voltage protection. That's the 2 industry terms.
Hold on. Well, if it's 2-wire circuit, you still have low voltage protection. No,
you call it no voltage. You got to have no voltage before it's going to drop out.
Why would wouldn't a coil drop out at 2 wires? Whether if the low voltage is low voltage.
Yes, you're right, Mike. It will drop out, but it won't stay dropped out.
It'll chatter.
Right. Let's say you have a brownout for a certain amount of time.
Now here's an example. I've seen this happen. All right, a motor starts, 2-wire circuit. When the motor starts, it starts drawing current, so what happens to the voltage? The voltage goes down. Well, it gets down below the coil because the coil is being connected onto the motor circuit. Well, now the voltage goes down. Well, because the voltage goes down, then it drops out the coil, but 2-wire circuit. Well, now the voltage dropped out the coil, it dropped out the motor. Well, what happened to the voltage?
Goes back up.
Well, the voltage goes back up again because you dropped out the load off of the circuit that you tapped on, which was the motor.
Yeah.
All of a sudden, the motor starts again. Well, then the coil kicks in the contacts, and the motor starts to run again. But all of a sudden, guess what? Well, now it has under voltage because the voltage dropped. Then it goes back and forth, back and forth, back and forth. So there is no voltage protection. And I understand that concept. I'm trying to tie in these industry terms with the logic that it approaches. So we have no safety protection on a 2-wire circuit, right? Because it restarts. A guy could be, I mean, how many times have you guys read in newspapers where this happens a lot in concrete plants, and people get into drums all the time, and this power goes off, and a guy figured, oh, well, you know, power's off, so now it's time they jump inside these concrete things, and they start beating all the concrete off the inside of these tubs, and all of a sudden, power comes back on again, and the guy's inside this great big grinder, and all of a sudden the guy gets just all chopped up because it was a 2-wire control circuit. 3-wire control circuit would have prevented that from happening because you can't start that until you press the start button. Plus, the 3-wire gives you the ability that once you have low voltage and the coil drops out, which protects the motor, well, then the motor's not going to restart again until you manually go back in again. Anybody have any comments on that? No? All right, let's talk about some exercise for reading wire diagrams. And I think we've already done this, but I'll just do it one more time. Okay, line 1 here is the line side of the stop. That's the wire coming in, point 1. Okay, I got that there. And then this is the load side of the stop. Okay, well then that would be that point right there. And then the load side of the stop, so we have line 1, and we go to 2. 2 supplies the load side of the stop and the line side of the start. So 2 is the load side of the stop and the line side of the start. 3 is common to the coil and common to the load side of the start. So 3 is common, it goes to the coil, which we can't see, but it goes to the load side of the start, helping us kind of like just kind of tie together there.
It's kind of like the hand-drawn diagram, because you know if you have a stop station, you need to connect it to, or you look at your line diagram, you know that you have to connect the load side of a stop switch to the power supply.
I guess this is a mental point, is that right?
Yes.
Mentally you're saying, okay, that's there.
It's like you could
That's
do this
there,
without the numbers.
That's there. Yeah, okay, without the numbers.
Kind of.
Kind of like, well, that point is there. All right. Multiple start-stop push buttons. That was Mike Corbett jumping in on there. Additional start-stop stations can be added to a 3-wire circuit. Let me tell you something. I can definitely hook up a 3-wire circuit right now. I'm not saying I'm getting sick of it, but I'm getting really close to being sick of this 3-wire circuit right now. I think I like the 2-wire circuits, but I can hook up a 3-wire circuit with auxiliary contacts and understand how the overloads work out. If I see another 3-wire circuit coming up here, I hope we can get off these 3-wire circuits. All right. All right. I want to add some multiple stops and starts to a 3-wire circuit. I know the advantages of them. Well, if you put a stop button in series with the whole process right here, then any stop button would obviously drop out the voltage to one side of the coil, which drops out the coil. Put the start button in parallel to the multiple start buttons. Any start button would get voltage to the one side of the coil, and the other side is already there, which would energize the coil. And you're saying, well, numbers don't mean anything. Understand the process. Know you're connecting things in series if you're trying to stop it, connecting things in parallel in this application here if you're trying to start it. I got it. Okay. Now, how do we actually really do this? How do we run the wires? What do we got here? We got disconnect. 3-phase conductors going to the motor. To the starter. 3-phase conductors leave the starter. Traveling down to the motor. T1, 2, 3. Got it. Now push button. I'm picking up my control conductors, apparently, tapping off the line side of the contactor. So, I'm running 3 wires. So 3-wire control. Let's see what happens here. 1 wire goes over to the one stop, and the stops are connected in series with each other. Then I supply the one start, and I continue the one start, the other start, so we're providing power to both start buttons. And that's the number 2. And number 3 is any one of these start buttons would give me power to 3, and 3 I know is the coil. 2 is the auxiliary contact. I can visualize that. So this is what you'd have to do, draw this out. And even if you draw it out, then you have to then test it. Push this button here, follow how the currents travel as we show the different circuit.
Well, and here's the thing, Mike. If you go back to the previous slide, I mean, you have your ladder diagram. And typically this is what you're going to get from the architect or the engineer. And then when you get out there to the field, you go to the last slide that we were at, this is what you see out there in the field. You've got your start-stop stations, and one's 25 feet away from each other, and you got to run this conduit between the junction box and the start-stop stations. Then you've got to run your conduit from your disconnect to your motor starter, which is another 50 feet, and then your motor starter's 25 feet from your motor, and your start-stop stations are 50 feet from the motor, and so everything's all over the place. And you get all this wire out there and you get it pulled, and then you start scratching your head going, this doesn't even look like my ladder diagram, because the physical relationship of what you see here on the ladder diagram is not the same than what it is in the field. And so you've got to start to be able to put all that stuff together and go, oh, now I've got 200 feet of wire pulled, and now I see what's going on and how everything's functioning.
Well, when I was an electrician, I enjoyed pulling wire. I can't explain why. I love circuitry. I love with the combinations and where you can drop off these wires here and continue these. I love not making splices, pulling wires through whenever possible. I just found that to be a challenge. And you had to really think ahead. What were you trying to accomplish? What wires and what colors? Because color coding was important to me. If this was going to be a switch leg, or if this was going to be a feed, if I wanted to drop something off here, did I want to put a loop here? That would have run through that there? What was I trying to achieve? And you had to really think this thing out, and how you were going to do it in advance, and how did you run the pipe? Well, you had to know how you wanted to pull the wire before you ran the conduit. And then you ran the conduit, and then you had to visualize and know, okay, I'm pulling the wire, got a snake, I had snake in both ends. I'm pulling this one, I'm pulling that one in there. I had to know, okay, this one, drop off the 2 colors here. Okay, pull these other ones through. Okay, pull these back here. Boom, 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 boom. And then you get it back. But I was able to visualize in advance before I ran the conduit, before I pulled the wire. Good point. Steve, you going to say something?
I was just going to say, and if the engineer doesn't give you a riser diagram like this, and if you're just working from a line diagram, this is where you're going to have to do your hand drawn and come up with that riser on cardboard out on the
Right.
job if it hasn't been done.
I would have to do this on paper. There's no question about it. I would have to draw this out on paper, and just like I see on the graphic on the left-hand side, the number hash marks inside here, I'd know exactly what I'm doing, and I'd want to know my colors. What colors am I trying to achieve? Because if I'm using if black is going to be supplied to my stop buttons, then that'll be my standard. By the way, is there any color for control wiring that people are using for a start 3-wire? Is there anything, any
No.
practice at all?
I don't know of any real industry
Do you have a practice yourself, though, Dan?
standard, but I have a practice that my journeyman taught me back when I was an apprentice.
Let's hear it.
Was that all the wires coming back from your start buttons need to be bright colors, and all the ones coming back from the stop would be the bright colors. So all the ones headed for terminal 2, and then all the ones from the start buttons would be the duller colors, like a brown. So you'd have like an orange wire coming from your stop and a brown coming from your start.
Right here. Stops would be what color?
Would be the brighter colors. So it'd be like a red, orange.
Okay. And then the 2s would be what?
Would all be the bright color, and then
All bright colors.
the 3s would all be the duller color.
Okay. All right. All right. That's just the system, right? All right. 3-wire control circuits. Another 3-wire control circuit. You got to be. Oh, good. At least it's supplied by a transformer. Something different. Don't tell me you don't know 3-wire control circuits by now. Control transformers are frequently used in motor controls to provide greater safety to personnel by using reduced control voltage. All right, let's see what we got here. All right, we got a 480-volt system. Line 1, 2, 3 coming in, main contacts in the motor, da-da-da-da-da-da-da, T1, 2, 3 going to the motor. These are my overloads. All right, I want to operate a 120-volt control circuit, so I put a transformer. Now, do I put a transformer, or do I just buy a starter that has a transformer and the primary is already pre-wired with the fuse protection. Is that the way it is?
Yeah.
Okay, let's talk about the way it really is most of the time. Steve?
Depends on your application. You may be picking up your control circuit from some other remote place like an air handler.
No. I'm saying off a transformer.
Yeah, but the control circuit may be in a transformer in another piece of equipment that is going to control your starter if you're interlinking systems.
But is the transformer there?
Could be.
Is it already pre-wired, the primary? And you just have the terminals for the secondary? How often do you go, would you buy a transformer and put a transformer 480 to cut it down to 120 for your control wiring?
Well, if you're starting from scratch, you're going to try and get it in the bucket with the starter if you're designing it.
That's what we're talking about.
Yeah, if you're
Talking about
able to
today, a
design
guy
from
going out
scratch.
today, if you're going to have a 120 volt control with a 480 volt starter, is the Dan?
In the, you'd have to know your control scheme before you buy your MCC. So
Right.
if you wanted to use that in your control scheme, you would order them in the MCC.
All right, so the practice would be you need to understand your equipment. And if you want to operate 120 volt controls and you got a 480 volt contactor, or a starter rather, you're going to make sure your starter comes with a transformer already pre-wired. And you're just going to come off the 120 volt terminals, the X1, X2. Am I right about that?
Yes.
Okay, so therefore we will show all this in black on the primary with the fuses because that's going to be by the manufacturer. The X2 would be in black because that's also by the manufacturer taking care of that side of the circuit. And then we just go back to our standard. Now, I don't understand this. We're going to talk about this tomorrow, but I don't think there's any fuse protection on the secondary, is there?
There's normally one.
There is fuse protection on the secondary,
Yes.
as well as fuse protection on the primary?
Yes.
All right, we'll talk about that in the next DVD. All right, so we're just saying that you're able to drop down lower voltages. The best thing is get your equipment with a transformer already pre-installed. And what do we got here? Here's a different way of looking at it. Here's my line 1, line 2, primary side. I'm going to have that in black. Here is my X2 going over to the M coil. I have that in black because that's already done by the manufacturer. Are the fuses, if you buy one, are the fuses already there? The primary fuses and the secondary fuses?
Yes.
All right, so that'll all be black. The primary and secondary coil and the fuse will be black because that's there. I'm just coming off of X1, going over to my stop in series with my start, which is in parallel with the auxiliary contact, and I'm just going to be running my 2-wire, my 3-wire, and my 1-wire. Right? So whether it's 480 to 120, it's not that big of a deal. It's still the same basic 3-wire control circuit. All right, 3-wire control circuit with a neutral. No, it's 120 volts, so it is a neutral. I mean, using that example. Again, we'll have this already color-coded, so they're all black, whatever it's not, it's all by whatever's pre-wired. And the neutral conductor comes off of L2, which is connected to the coil. Now, the code actually says that you cannot use a neutral conductor for any kind of control. And the reason being is because if we took the hot wire and we connected a hot wire to, let's say, the one side of the coil, and then we use a neutral conductor to the other side for the control, if there was a short of the neutral conductor to one of the other wires, you could bypass all the safety protection of a 3-wire control circuit by bypassing all that, and then of course the coil could be energized, the motor could run. But I got to ask you a practical question, whether this is just a waste, whether this is a great theoretical concept, you don't use a neutral for control. Isn't it already, watch this, if this is black on the primary, because that's manufacturer, if the transformer secondary is black as a manufacturer, if the secondary neutral with the overloads is black as it's a manufacturer, if the X1 to the fuse is black with the manufacturer, then is it a no-brainer that you're not going to be using a neutral for the control circuit? There's no way to physically do it, just the way you buy the starter?
Right. What happens a lot of times is if you have a starter bucket, sometimes it's called that, with everything included, then the field wiring is attached to a terminal strip or a barrier strip that's in the manufactured product.
Right.
And so you're only going to be connecting external wiring to the barrier strip in the equipment.
Right. All right, but let's just review this again. If you somehow use your neutral portion, because the neutral is going to be grounded here, if you use a neutral as part of your control wiring, you could have a fault to the neutral to another conductor that could bypass the start button, and it could cause the motor to start and run, and you have no way to stop it, no way to control it. One of the things I want to talk about in the next DVD is safety. Have you guys ever heard of an experience where you had a failure of a neutral that caused a restarting of a motor or a running of a motor? Anybody?
No, because we don't wire them that way.
Well, there you go. Okay. Simply solves that problem. All right. Option of using a 2 or 3 wire circuits in one diagram. It's common to have a line or a connection diagram that shows connection points for both 2 wire and 3 wire circuits. No, not another 3 wire circuit. Okay, so here's my connection diagram. And okay, it's showing a dotted line that here's the option. If you want to, you can use a start stop between points 1 and 3. Or don't use a start stop. Optionally, put a 2 wire control circuit. That's what we're trying to do. Go from line 1 to line 3. That coil is going to operate. And let's see. This line 2 is going to be black because that's already pre-wired. All right. And then here's your 2 wire control circuit, 1 to 3, 1 to 3. Here's the start stop. That's fine. And I think this is just showing what it would look like, the wiring diagram inside the actual contactor itself. On the diagram given on that. Now, Dennis, we got something over there at the end of that table. What's
Well, and this is what Eric brought was basically an MCC bucket, and we're kind of hoping that there was a transformer in there, but there's not one in there. Oh, but Eric's got a transformer, I think, in front of him that would physically go inside this bucket.
But wouldn't you have to get equipment that is designed to use a specific transformer by that manufacturer and to be installed in that equipment?
Yes.
You can't now start going
Right.
in and dropping transformers in there. In other words, the step down voltage is part of a whole package that you're going to be getting if you're going to be doing that.
Well, and there again, you want it UL listed. So that's why you have the manufacturer build it as one complete unit. Then they put the UL stamp on it and it's UL listed.
I never worked in the industry. I worked in commercial, I worked in residential, multifamily. I didn't do hardly anything in controls except screw up a 2-stage thermostat and get fired. I mean, that was almost, yeah, pretty much my total control experience. But my perception is that today we're having equipment that really works together better. You're able to buy the contactor. It's already pre-wired. It has the fuses inside there. It has a transformer inside there. You know, you're not having to like make things work. Is that a fair statement compared to maybe what it was 40 years ago, 30 years ago? Or no? Is it similar?
Well, most industry, like our industry, we have some relatively new and some new equipment. We have some relatively old, like 40 and 50-year-old switchgear.
But is the 40,
And there
50-year-old
is-
switchgear something that people piece together to make things work, and today it's more already built together as a component?
Well, it was built new in 1964,
Okay.
particular ones I'm talking about.
Okay.
And they've been made to last. I mean, we replace what needs to be replaced. If we decide we need a transformer in one, we'll install one that
Okay.
would be correctly sized. And
Okay. All right. Let's talk one thing, because I'm going to forget about the overloads on my boat lift. 3 motors, $1,200 cost me on that. Finally, one day I decided, and by the way, I skied with a barefoot buddy of mine at the time. He was an electrical contractor, and after, we skied for years, and after 3 motors, $1,200, I said, you know what? Do me a favor, bring me a 30 amp disconnect. Let's go nameplate rated motor. Motor drew I think 6 amps, little tiny, whatever, quarter horsepower, half horsepower motor, drew 6 amps. He got me a 30 amp disconnect, and he couldn't get me whatever 125% of 6 was, which was 7 amp fuses, or they make a 7 amp fuse, I think, but they just didn't have it in there, or didn't have a 6, whatever it was. He had to get me a fuse that was lower than the nameplate rating of the motor. And I'm thinking, well, put it in there, let's see what happens. If not, we'll just jump it, we're still gonna go skiing, you know what I mean? But put that in there. I think he put like a 4 amp fuse on a motor that drew like 6 amps, because that's all I got. You know that motor worked fine? I was shocked. A 4 amp fuse I could have put on that motor. My buddy was he was a barefooter, an electrical contractor, but even if I hired an electrical contractor, let's say I wasn't, you know, an electrical person, and I paid $200 to put a disconnect with a 4 amp fuse to protect a 6 amp motor, it would have saved the customer, in my case, me, $1,000. And what I learned a lesson was that if you provide overload protection with fuses, we're not talking about a contactor and a starter and all the assembly. We're just talking about a fusible disconnect. And you size the fuses, like you were saying, Dan, you size it at 100% first to see if that's going to work. If you get a fusible disconnect, and let's assume we didn't need any controls at all. I just got a fusible disconnect, and there's the motor right there. Size the fuses at 100% of that nameplate rating. Stick those fuses. If they don't fit in there, get the smaller size fuse, stick it in there. And if your only control is to close the switch for that motor to run, and when you want the motor to stop, just open the switch. That gives you your overload protection. At the same time, that can give you a short circuit and ground fault protection at another level. And that was a lesson that I learned. It's really important to provide overload protection as close to the nameplate rating of that equipment. It really will pay for itself in the long run. We got a slide here, the last slide on this particular DVD. Dennis, tell us about, you know, what you do with this.
Well, these are the simulator boards that I've basically put together, and I've got 2 contactors in them. I've got 3 relay bases that I can put on delays, off delays in, 2 ice cube relays. The keyless fixtures there representing the motors. I have a fuse disconnect, or a fuse there to just kind of
Is that a
back
fuse
up.
right there?
Yeah, it's a fuse block
Okay.
right there, which I put in. You know, if somebody shorts something out, then at least it's going to blow the fuse and it's not going to trip the main breaker. On the right side is all the patch cord plug-ins. Then I've got some control lights on the upper right. Then I've got my start-stop stations. I've got a handoff auto. And then I've got 2 toggle switches to represent high-low level switches and that kind of stuff. And the process here, the guys have to troubleshoot where all the patch cord plug-ins go first. They have to find out if they go to the contactors, if they go to the keyless, if they go to the relays, if they go to the start-stop stations.
Is this right here? What are these? Is this?
Those are the patch cord plug-ins,
Okay.
okay? And banana cords is what you want to use there. And so they have to troubleshoot and find out where everything is. So then that way they get an idea of how a piece of equipment actually works and what it does. Then I've got set up ladder diagrams that they can actually physically go through there and hook up, and they can actually see how everything starts to function, like your start-stop station with your magnetic coil and things like that.
Steve, you taught motor control for how many years?
19.
19 years. Did you make up something like this in a lab for yourselves, for your students?
I wish I had a good picture of that. Maybe I can get one tomorrow. But we built up a frame about 4 foot by 2 foot table, and had a steel tube frame and a plexiglass top, so you could see down through it and see the wiring underneath it.
Oh,
And
that's kind of cool.
Yeah, and then we just drilled holes in the top for all the push buttons and switches and so on in the top, and had a couple motors down underneath, a couple small single-phase motors that they could actually hook up and see them run, and then just pilot lights and things to simulate different activities. And some of them we even had a small PLC on them and put that all together. So I'll have to see if I can get a picture of those. They worked real well.
Well, I think the point is, those of you that are instructors and those that go to students, that instructors, maybe you can encourage your instructor to put together something.
Yeah.
And, you know, Dan, what you might put together as an instructor might be different than what Steve is going to put together, because your needs are differently, what you're looking to achieve and what you're looking to communicate, because different parts of the country achieving, looking to achieve different things. Well, we're done at the end of this DVD, but before I close on this particular one, anybody have any parting comments, any one thing that you want these guys to try to remember at this point? Steve?
Three-wire controls are simply normally closed stops in series, normally opens in parallel. And you can put any number that you want to. Just get your series and parallel relationships.
Eric?
It may not seem like it, but learning this stuff really does make your life easier. Now, had you learned about all this stuff before your boat lift, you could have saved yourself a lot of trouble. So it may seem to the student at the front end, oh my gosh, this is a lot of work. But the reality of it is that it's more work if you don't learn it. And if you do learn it, you become the go-to guy for your company.
I like that, and I think that's an important point, and that is that you're the go-to guy. You're the person that people have to ask questions. Dan, anything you can just tell the guys for today?
Well, the three-wire circuit that we've talked about and that you're almost sick of
I am sick.
is basically the building block for hardwired circuits and PLC circuits.
So if I have, and I think I got 3-wire circuits and mentally 2-wire circuits, I mean, I got it down. Are you saying that that's really going to give me the basic that I need, that when I go to the other stuff, it's going to be fine?
Yes, that's the foundation that you'll build on.
Yes.
Dennis?
Again, go back through the book, go back through the units that we've already covered. And then if you have any further questions, just go back through the DVD itself and re-look at those certain points that you feel that you're still weak on, and I think that'll help quite a bit.
Well, we did it. We did the first part. And it's a building block. We're going to go one more DVD, and we're going to put some of the stuff together now, and garage door openers and some other examples. We're going to talk a little bit about safety. Tomorrow, we're going to just be, putting this whole package together, lockout, tag out, some other important things. Thank you so much. Take a break, do what you got to do, and we'll see you on the next DVD. God bless.